What if the most fundamental truth about our universe isn't about matter or energy, but about code? What if everything we see, touch, and feel is a product of computation? It's not science fiction. It's a question that has quietly emerged from the frontiers of physics, computer science, and philosophy. Could we be living, not in a physical universe, but in a simulation governed by quantum rules? At first glance, this sounds implausible. Yet over the last century, physics has slowly chipped away at our classical understanding of reality. The deeper we peer into the quantum world, the less solid the universe becomes. Particles behave like waves. Outcomes remain uncertain until observed. Information, rather than matter, seems to lie at the heart of it all. This documentary explores one of the most provocative scientific ideas of our time, the quantum simulation hypothesis. There are questions that fade over time, curiosities that are answered, settled, or simply forgotten. But there are others that persist. They return in new forms, shaped by each generation's science, technology, and understanding of the universe. What is reality is one of those enduring questions. Today, it reappears in a startling new frame. Could our universe be a simulation? The idea may sound modern, even futuristic, but the roots of this question are ancient. More than 2,000 years ago, in a cave imagined by the philosopher Plato, prisoners watched shadows cast on a wall, mistaking them for reality. The scene was a metaphor, a warning that our senses might deceive us, that the truth could lie beyond what we directly perceive. In the 17th century, René Descartes questioned the very reliability of experience, imagining that all of reality could be the illusion of a powerful deceiver. The common thread through these thought experiments was the suspicion that what we perceive may not be the full story. For most of human history, these questions remained in the realm of philosophy. But beginning in the early 20th century, physics began to provide its own unsettling answers. With the birth of quantum mechanics in the 1900s and 20s, reality itself became unstable. Classical physics, the sturdy framework built by Newton and refined over centuries, was found to break down at the smallest scales. Suddenly, electrons did not move in predictable orbits. They existed in clouds of probability. Particles could behave like waves. Observing something appeared to change its behavior. This wasn't just theoretical. The experiments were real, repeatable, and undeniable. At the heart of the revolution was the double-slit experiment. In its earliest form, light was shone through two slits in a barrier and onto a screen. Instead of forming two bright spots, as particles might, the light created a pattern of interference, as if it had passed through both slits simultaneously, as a wave. But when detectors were placed to measure which slit the light actually passed through, the interference pattern disappeared. The very act of observation seemed to collapse the wave-like behavior into a particle-like outcome. This was no illusion. It was an empirical result, verified over decades and extended to electrons, atoms, even some molecules. And it led to a disturbing implication. The observer plays a role in defining what is real. For many physicists, including Niels Bohr and Werner Heisenberg, this was simply the new nature of reality, uncertain, probabilistic, observer-dependent. But for others, including Albert Einstein, it was deeply troubling. "I like to think the moon is there even if I am not looking at it," he famously said. Einstein believed there must be hidden variables, unknown factors that made quantum outcomes look random when they were really deterministic. But his efforts to prove this through thought experiments and mathematical challenges never fully restored the classical view. Over time, quantum theory became one of the most successful scientific frameworks in history. It underpins modern electronics, lasers, nuclear energy, and countless technologies. Yet it also deepened the mystery. The more precisely physicists studied quantum systems, the more elusive the concept of objective reality became. Then came the turn of the 21st century, and with it, a new set of tools and concepts. Information theory, originally developed by Claude Shannon in the 1940s to improve telecommunications, gained new relevance. Some physicists began to wonder, what if the universe is not fundamentally made of matter or energy, but of information? What if particles and fields emerge from a deeper, informational substrate? This wasn't just metaphor. John Wheeler, a prominent physicist who worked with Einstein and Bohr, proposed that information might be the most basic building block of reality. He coined the phrase "it from bit," suggesting that every particle, force, and even space-time itself could emerge from binary choices, yes or no, 1 or 0. At the same time, computer simulations were becoming powerful tools in physics. From modeling galaxies to predicting quantum interactions, scientists were using computers to simulate complex systems with increasing accuracy. And with each advance came a deeper question. If we can simulate parts of the universe, could the universe itself be a simulation? In 2003, philosopher Nick Bostrom at the University of Oxford presented a formal argument that brought this idea into the spotlight. He proposed that one of the following 3 statements must be true. First, that advanced civilizations never reach the technological capability to run ancestor simulations. Second, that civilizations with such capabilities choose not to run them. Or third, that we are almost certainly living in a simulation. It was a startling claim, but logically sound. If even a small fraction of future civilizations were to run simulations of their past, creating digital worlds populated by conscious beings, then the number of simulated minds would vastly exceed the number of real, biological ones. Statistically, it would be more likely for any given conscious mind to be inside a simulation rather than outside one. The idea caught fire in public discourse. Figures like Elon Musk publicly supported the likelihood of simulated reality. Popular culture followed, with films, novels, and media playing on the concept. But among scientists, the conversation took a more careful path. Rather than debate whether we are in a simulation, physicists asked, what would that even mean? How would a simulation of the universe work? And could it be detected? Some researchers began to explore how quantum mechanics might actually hint at a simulated structure. If the universe were computed, perhaps quantum uncertainty reflects limits in processing power. Perhaps entanglement, where particles instantly influence one another across space, reveals shortcuts in an underlying code. And if space itself is quantized, like pixels on a screen, maybe high-precision measurements could reveal its discrete nature. Other scientists remained skeptical. They argued that the simulation hypothesis, while intriguing, lacked predictive power. It could not be tested in the same way other scientific theories could. It risked becoming a metaphysical story, interesting but unfalsifiable. Still, the question persists. It persists because it is tethered to real observations, quantum uncertainty, entanglement, and the strange role of information in physics. It persists because each new breakthrough in quantum theory, computing, and cosmology adds another layer to our understanding of reality, and sometimes another layer of uncertainty. Long before atoms, quantum fields, or simulated worlds were part of scientific discourse, people looked at the stars, the sea, and the mind, and asked a fundamental question: what is real? What lies behind the appearances of the world? Is what we see the truth, or merely a shadow of something deeper? To understand where our modern questions about reality come from, we must turn first to philosophy. This is not a detour, but a necessary step. For centuries, before physics emerged as a distinct science, the exploration of reality belonged to philosophers, and their insights still shape the questions we ask today. One of the earliest and most influential voices in this story was the ancient Greek philosopher Plato. Writing in the 4th century before the Common Era, Plato described a thought experiment that continues to resonate in modern discussions of reality. It is known as the allegory of the cave. In this allegory, a group of people are imprisoned from birth in a dark cave. They are chained in place, facing a blank wall. Behind them burns a fire, and between the fire and the prisoners, other people walk along a raised path, carrying objects and casting shadows onto the wall. The prisoners, having never seen the real objects or the world beyond the cave, come to believe that the shadows are the only reality. The world, to them, is two-dimensional and silent. They do not know the fire, the people behind them, or the sunlit world outside the cave's entrance. Now imagine that one prisoner is freed. At first he is confused. The fire hurts his eyes. The shapes behind him are unfamiliar. But as he adjusts, he begins to understand. Eventually, he is brought out into the sunlight, into the true world, and he sees reality as it actually is. If he returns to the cave, the others may not believe him. They may even resist the idea that what they see is not all there is. Plato's point was clear. Human perception can be limited, and what we take for reality may be only a projection of a deeper truth. The journey out of the cave symbolizes the journey toward knowledge, reason, and philosophical insight. Though Plato had no concept of atoms, simulations, or quantum fields, the underlying idea that what we perceive might not be the full picture remains deeply relevant. Centuries later, in the 17th century, René Descartes would revisit this theme in a new form. Descartes lived during the rise of scientific revolution in Europe, a time when long-held beliefs were being challenged by astronomy, mathematics, and empirical investigation. Yet Descartes took a radical turn inward. He asked, how can we be certain of anything at all? In his Meditations on First Philosophy, Descartes stripped away all assumptions. What if everything he believed, everything he saw, felt, or remembered was false? What if, he proposed, some powerful deceiver were feeding him false experiences, manipulating his thoughts and senses? In such a case, how could he trust even the most basic facts? Out of this mental exercise came Descartes' famous conclusion, cogito, ergo sum, I think therefore I am. Even if he were deceived about everything else, the very act of doubting proved that he existed as a thinking being. It was the one truth that could not be denied. Descartes' deceiver is often compared to modern ideas of virtual reality or computer simulations. If a sufficiently powerful system could generate experiences indistinguishable from the real world, how would we know? Would we have any way to step outside and confirm what was real? While Descartes' questions were philosophical, they anticipated many of the concerns that modern scientists face when grappling with quantum mechanics, perception, and consciousness. His focus on doubt and verification would later influence scientific methodology itself. In the centuries that followed, reality came to be defined more and more by physical laws. The universe was understood as a machine, running smoothly and predictably. Isaac Newton's laws of motion and universal gravitation, published in the late 17th century, created a framework where cause and effect reigned. Under this view, reality was objective, absolute, and governed by mathematical relationships. If you knew the initial conditions of a system, its position, mass, and velocity, you could predict its future with complete certainty. This Newtonian worldview dominated science for over 200 years. It provided the foundation for engineering, astronomy, chemistry, and much of physics. But it also brought with it an implicit assumption that reality was knowable, external, and observer-independent. The universe was not shaped by our presence, it simply was. That assumption began to crack in the late 19th and early 20th centuries. The rise of thermodynamics, electromagnetism, and especially quantum theory revealed that the universe was not always so orderly. At very small scales, particles behaved in strange and unpredictable ways. Outcomes could not be forecast with perfect accuracy. Observations seemed to affect the system being measured. Suddenly, the clean lines of Newtonian certainty gave way to a haze of probability and paradox. Meanwhile, questions about the nature of consciousness remained unresolved. In the late 19th century, figures like William James and Henry Bergson debated whether human awareness could be fully explained by physical processes. Could brain activity alone account for thought, perception, and emotion, or was there something more fundamental at play? In the 20th century, as psychology gave way to neuroscience and cognitive science, new approaches emerged. Scientists began to map the brain, analyze neural pathways, and model behavior. Yet the so-called hard problem of consciousness, the question of how subjective experience arises from physical processes, remained elusive. These threads, philosophy, physics, perception, and consciousness, converge in the modern debate about simulation. If reality is not fixed, if observation affects outcomes, and if experience itself may not reflect objective conditions, then how do we define what is real? Is it what we measure, what we perceive, what we can reproduce in a model? Today, this question takes on new urgency, not just because of physics, but because of technology. Virtual reality systems can now create environments that mimic the physical world. Artificial intelligence systems are beginning to emulate human decision-making. Simulations are used in weather prediction, molecular modeling, economic forecasting, and space exploration. And with each advance comes a new blurring of boundaries. When a physicist runs a simulation of the early universe on a supercomputer, they are not just imagining the cosmos, they are creating a virtual analog governed by mathematical rules. The closer these simulations come to matching real observations, the more difficult the distinction becomes between a model and a world. But a key difference remains. In our simulations, we are the creators. We set the rules, define the parameters, and determine what exists. If our universe were a simulation, then we are not the creators. We are the inhabitants. And the rules we discover may not be the ultimate ones. They may be constraints imposed by an underlying system beyond our reach. This leads to an unsettling yet powerful possibility that our deepest scientific investigations into space, time, particles, and consciousness may be probing the architecture of something designed, not by intention necessarily, but by construction. At the dawn of the 20th century, the scientific community stood upon the solid ground of Newtonian physics. The universe was thought to be mechanical, deterministic, and fully understandable through the lens of classical laws, but cracks had begun to appear in this vision. Certain experimental results, particularly involving light and matter at very small scales, simply refused to align with existing theories. These early anomalies gave birth to what would become the most counterintuitive and transformative branch of physics ever developed: quantum mechanics. The story begins with an unsolved problem that plagued physicists near the end of the 19th century: how objects emit and absorb radiation. Specifically, scientists were trying to understand blackbody radiation, the way a perfect absorber of heat emits light across different wavelengths. Classical theories predicted that as the wavelength of light approached the ultraviolet end of the spectrum, the energy emitted by a blackbody would become infinite. This was called the ultraviolet catastrophe, and it was not just a mathematical glitch. It indicated that the prevailing theories simply broke down at small scales. In 1900, German physicist Max Planck made a revolutionary proposal. He suggested that energy is not emitted continuously, as classical physics claimed, but in discrete packets. He called these packets quanta. To make the equations work, Planck introduced a new constant, now known as Planck's constant, to describe the size of these energy quanta. At the time, Planck himself saw this as a purely mathematical trick, not a statement about the nature of reality. Yet his formula matched experimental data perfectly. Without fully intending to, Planck had opened the door to a new realm of physics. A few years later, in 1905, Albert Einstein took this idea even further. He proposed that light itself is made up of discrete packets, later called photons. This was part of his explanation for the photoelectric effect, where light hitting a metal surface can eject electrons. Classical wave theory could not account for why only certain frequencies of light could release electrons, regardless of intensity. Einstein's photon model solved the mystery, earning him the Nobel Prize in Physics in 1921. These early findings challenged the long-held view that energy and light were continuous. They hinted at a universe that operated on rules very different from those of classical physics, especially at the atomic and subatomic levels. But things were about to get even stranger. In the 1920s, Danish physicist Niels Bohr developed a model of the atom that incorporated quantum ideas. He proposed that electrons orbit the nucleus in fixed energy levels and can jump between these levels by absorbing or emitting a photon of a specific energy. This model successfully explained the spectral lines of hydrogen, which classical physics could not. Yet it raised new questions. Why do electrons only occupy certain orbits? Why don't they spiral into the nucleus? To answer these questions, other physicists began developing a more comprehensive mathematical framework. In 1924, French physicist Louis de Broglie proposed that particles like electrons might also have wave-like properties. This idea, known as wave-particle duality, would soon be confirmed by experiments. In 1927, Clinton Davison and Lester Germer at Bell Labs showed that electrons fired at a crystal surface produced interference patterns, just like waves of light. At this point, it was no longer possible to view matter and energy in purely classical terms. Particles could act like waves. Waves could act like particles. The boundaries between categories were breaking down. This new view of reality needed a new mathematical language. In the same year, two competing formulations of quantum mechanics were developed: matrix mechanics by Werner Heisenberg and wave mechanics by Erwin Schrodinger. While the mathematical approaches were different, both produced the same results and described the same physical phenomena. Together, they formed the foundation of modern quantum theory. Heisenberg's formulation emphasized observable quantities and introduced a radical concept: uncertainty. In 1927, Heisenberg published his famous uncertainty principle, which stated that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. The more accurately one is known, the less accurately the other can be determined. This was not due to measurement flaws or technological limitations. It was a fundamental property of nature. This principle shook the philosophical foundations of science. It suggested that the universe was not deterministic in the way Newton had imagined. Instead, at its core, nature was governed by probabilities. You could not predict exactly where a particle would be. You could only calculate the likelihood of finding it in a certain location. Schrodinger, meanwhile, developed a wave equation that described how the quantum state of a system evolves over time. His famous thought experiment, involving a cat that is simultaneously alive and dead until observed, was meant to highlight the absurdity of applying quantum principles to everyday objects. Yet this very absurdity revealed something essential. Quantum mechanics does not easily scale to the macroscopic world, and observation appears to play a central role in how quantum systems resolve into definite outcomes. By the late 1920s, quantum mechanics had become an established and powerful framework. It could predict the behavior of electrons in atoms, explain chemical bonding, and describe radiation with unprecedented accuracy. It was tested again and again, and each time, the results confirmed its strange predictions. But the success of quantum mechanics did not settle the philosophical debates it raised. Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper in 1935 arguing that quantum mechanics was incomplete. Their thought experiment, known as the EPR paradox, described two entangled particles that appeared to affect each other instantaneously, even when separated by large distances. This spooky action at a distance, as Einstein called it, seemed to violate the principle that nothing can travel faster than light. The EPR paradox was intended to show that there must be hidden variables, unknown factors that would restore determinism and locality to physics. But later experiments, particularly those inspired by physicist John Bell in the 1960s and carried out by Alan Aspect and others in the 1980s, showed that no local hidden variable theory could fully explain quantum entanglement. The strange predictions of quantum mechanics were upheld. This sequence of discoveries, from Planck's energy quanta to the confirmation of entanglement, marks the birth of what is often called quantum weirdness. It is a world where particles are also waves, where probabilities replace certainties, and where observation seems to influence outcome. And yet, this framework forms the backbone of much of modern science. Quantum mechanics is not just a theoretical curiosity. It underpins the behavior of semiconductors, lasers, superconductors, and countless other technologies. Without it, there would be no modern electronics, no GPS, no understanding of chemical reactions at the molecular level. Despite its strangeness, or perhaps because of it, quantum mechanics remains the most precise and successful theory in the history of physics, but its mysteries remain unresolved. Why does observation seem to collapse a quantum system into a definite state? What determines the outcome of a probabilistic event? And how can non-local entanglement be reconciled with the structure of space and time? Among the most profound and perplexing experiments in the history of science is one that appears at first glance deceptively simple. Take a source of light, a barrier with two narrow slits, and a screen to catch the light on the other side. Shine the light through the slits and observe the pattern that forms. This setup, known as the double-slit experiment, has been repeated in various forms for more than 2 centuries. And yet, with each refinement, it continues to reveal something unsettling, not only about the behavior of particles, but about the nature of reality itself. The story begins in the early 19th century with English physicist Thomas Young. At the time, the scientific community was divided over the nature of light. Was it composed of particles, as Isaac Newton had believed, or was it a wave, like sound or water? To investigate, Young performed an experiment in 1801. He allowed light to pass through 2 closely spaced slits, and then strike a screen behind them. If light were made of particles, one would expect two distinct bands where the light had passed through each slit. But that is not what Young saw. Instead, he observed a pattern of alternating bright and dark bands, an interference pattern characteristic of waves. This result supported the wave theory of light. When two waves overlap, they can interfere constructively, amplifying each other, or destructively, cancelling each other out. The pattern on the screen showed exactly this kind of interference. Light from one slit reinforced or cancelled light from the other, depending on the distance travelled. Young's experiment became a cornerstone of wave theory, and for more than a century, light was widely understood as a wave phenomenon. But as the 20th century unfolded, the nature of light, and indeed all matter, was thrown into question. Discoveries like the photoelectric effect and Compton's scattering revealed that light also behaved like a particle. Electrons, too, were found to exhibit wave-like properties. This duality, the idea that particles can behave like waves and waves like particles, became central to quantum mechanics. So what happens when the double-slit experiment is performed, not with beams of light, but with individual particles, like electrons, fired one at a time? In the mid-20th century, physicists set out to answer that question. They created setups where electrons were emitted one by one toward a pair of slits, with a detection screen placed behind. At any given moment, only one electron was in flight. And yet, as the experiment ran and more electrons were recorded on the screen, a familiar interference pattern began to emerge. This was astonishing. Each electron appeared to be behaving like a wave, passing through both slits simultaneously and interfering with itself. Yet when it was finally detected on the screen, it arrived as a single, localized dot, like a particle. Over time, these dots accumulated into the same interference pattern seen with waves. The implication was clear. The interference pattern was not the result of many particles bumping into each other. It was an intrinsic property of individual quantum objects. Each electron carried within it the potential to explore multiple paths, to interfere with itself, and to produce a pattern that only made sense in wave terms. But the mystery deepened when physicists added detectors to observe which slit the electron actually passed through. The moment a measurement was made, when the path of the electron was recorded, the interference pattern vanished. Instead, the electrons behaved like classical particles again, forming two bands behind the slits, just as Newton would have predicted centuries earlier. What changed? The apparatus, the slits, the electrons themselves. None of these were altered. The only difference was the act of observation. Somehow, the process of measuring the electron's path collapsed its wave-like behavior. The electron no longer explored both slits. It took one path or the other, and the interference disappeared. This result has been confirmed repeatedly, not just with electrons, but with photons, atoms, and even large molecules. The effect persists across different scales and materials. It is not a quirk of light or a failure of equipment. It is a window into the quantum world, a world where observation appears to shape outcome. But what does it mean to observe a quantum particle? Is it the involvement of a conscious mind? Is it the interaction with any measuring device? Does the universe somehow know when it is being watched? Physicists have wrestled with these questions for decades. Niels Bohr, one of the founders of quantum mechanics, argued that quantum properties do not exist in a definite state until they are measured. According to this view, known as the Copenhagen interpretation, particles do not have precise positions or paths until a measurement is made. They exist in a superposition of all possible outcomes, and measurement collapses this superposition into a single result. Albert Einstein, ever the realist, was deeply uncomfortable with this interpretation. "Do you really believe the moon is not there when you are not looking at it?" he asked rhetorically. He suspected that the theory was incomplete, that some hidden variables must determine the outcome, even if they were unknown to us. Others, like John Wheeler, embraced a more radical view. Wheeler proposed the idea of a participatory universe, where the act of observation is not just a passive recording of events, but an active process that brings reality into being. In one variation of the double-slit experiment, known as the delayed choice experiment, Wheeler suggested that a measurement made after a particle has passed through the slits can retroactively determine whether it behaved like a wave or a particle. In other words, future actions appear to influence past behavior. Experiments along these lines have been conducted, and while interpretations vary, the outcomes are consistent. Quantum systems behave differently depending on whether or not they are measured. The act of observation plays a crucial role, not just in what we know, but in what actually occurs. This has led some researchers to explore even more exotic ideas. Could reality itself be a kind of computation? Could the strange behavior of quantum particles reflect underlying informational processes, like those in a simulation? If so, the double-slit experiment might be telling us something not just about particles, but about the nature of the substrate on which the universe is built. To be clear, most physicists do not leap from quantum interference to simulation theory. The experimental data are robust, but the interpretations remain diverse and sometimes speculative. Still, the double-slit experiment stands as a gateway into quantum mechanics, a simple setup that reveals an astonishing truth. The universe does not always behave as if it is independent of the observer. This insight is not confined to laboratories. It echoes in cosmology, in information theory, and in the philosophical debates about consciousness and observation. It challenges our assumptions about objectivity and causality, and it forces us to ask a deeper question. If observation affects reality at the smallest scales, what does that mean for the universe as a whole? By the early 1930s, the core principles of quantum mechanics had been established. Particles behaved like waves, measurement altered outcomes, and the laws of probability replaced deterministic predictions. Yet the philosophical implications of these discoveries were far from resolved. Physicists continued to wrestle with questions that had no clear answers. What does it really mean for a particle to exist in multiple states at once? How does a potential become an actual event? And at what point does the uncertain quantum world give way to the concrete classical one we experience? It was in this atmosphere of unresolved paradoxes that Austrian physicist Erwin Schrödinger proposed one of the most famous thought experiments in the history of science, a hypothetical scenario that would become a lasting symbol of quantum strangeness. Known today as Schrödinger's cat, the scenario was designed not to explain quantum mechanics, but to illustrate what Schrödinger saw as a flaw, or at least a gap, in its interpretation. To understand the meaning behind the cat, we must first understand the idea it was meant to challenge: superposition. In quantum theory, a system can exist in a combination of states simultaneously. A particle is not here or there, it is here and there. This mixture of possibilities is known as a superposition. Mathematically, superposition is represented by a wave function which encodes the probability amplitudes for different outcomes. As long as the system is not observed or measured, it evolves according to the Schrödinger equation, maintaining all its possible states in a coherent, overlapping form. Only when a measurement occurs, when we interact with the system in a way that yields a definite outcome, does the superposition collapse into a single state. Before that moment, according to the Copenhagen interpretation, the particle has no definite properties. It is not simply that we do not know which state it is in, rather, it has no single state at all. To highlight the absurdity of applying this principle to larger systems, Schrödinger introduced his hypothetical cat in 1935. Imagine a sealed box containing a live cat, a vial of poison, a Geiger counter, and a tiny amount of radioactive material. The setup is arranged so that, within a given hour, there is a 50% chance that one atom of the radioactive material will decay. If it does, the Geiger counter detects the decay, triggers a mechanism that breaks the vial and releases the poison, killing the cat. If no decay occurs, the cat remains alive. According to quantum mechanics, the radioactive atom is in a superposition of decayed and undecayed states until it is observed. If we apply the same logic to the entire system, then the cat itself must also be in a superposition, simultaneously alive and dead, until someone opens the box and checks. This conclusion seems grotesque, even absurd. Cats, after all, are not quantum particles. They are macroscopic beings, firmly anchored in the classical world. Schrödinger's point was to show that the Copenhagen interpretation leads to a paradox when extended beyond the microscopic realm. At what point, he asked, does a quantum system become classical? When does the wave function collapse? And what constitutes a measurement? The thought experiment quickly became a lightning rod for debate. Physicists and philosophers offered various interpretations, each attempting to resolve the apparent contradiction. Some suggested that the cat is never truly in a superposition, only the observer's knowledge is uncertain. Others embraced the paradox, arguing that reality itself remains indefinite until observed. One alternative view emerged from the many worlds interpretation, first proposed by Hugh Everett III in the 1950s. According to this interpretation, the wave function never collapses. Instead, all possible outcomes occur, each in a separate, branching universe. In the case of Schrödinger's cat, one universe contains a living cat and another contains a dead one. Both outcomes are real, but they exist in parallel realities that do not interact. The many worlds view avoids the problem of wave function collapse, but at the cost of positing an infinite number of parallel universes. It remains a topic of philosophical debate and theoretical research, but it cannot yet be tested experimentally. Still, it illustrates how a single thought experiment can open vast conceptual doors. Another approach is offered by objective collapse theories, which modify the Schrödinger equation to include a mechanism for wave function collapse as a real physical process. According to these models, superposition is allowed only up to a certain scale or mass. When a system becomes sufficiently large, or when a sufficient number of particles are involved, the wave function collapses spontaneously. The cat, therefore, would be either alive or dead before the box is opened, not both. One such theory is known as the Ghirardi-Rimini-Weber model, proposed in the 1980s. It suggests that the collapse of the wave function is a stochastic process that occurs randomly but more frequently in larger systems. These ideas are still under development and remain outside the mainstream, but they offer a way to bridge the gap between quantum and classical worlds without invoking observation or consciousness. Speaking of consciousness, some interpretations go even further and propose that the presence of a conscious observer is necessary for collapse to occur. This idea, associated with physicists like Eugene Wigner and John von Neumann, suggests that consciousness plays a fundamental role in determining the state of a quantum system. While intriguing, these proposals face criticism for being vague and difficult to test, and for placing a poorly understood phenomenon, consciousness, at the center of physical theory. The debate surrounding Schrödinger's cat reveals more than just a scientific puzzle. It exposes the philosophical depth of quantum mechanics. At its core, the paradox asks us to reconsider what it means to know something, and whether things exist independently of our knowledge of them. It blurs the boundary between epistemology, the study of knowledge, and ontology, the study of being. In practical terms, the thought experiment also inspired new lines of research. The development of quantum computing, for instance, relies on the principle of superposition. A quantum bit, or qubit, can represent both 0 and 1 simultaneously, offering computational power far beyond that of classical bits. Understanding how and when superposition collapses is central to building stable, scalable quantum systems. Experiments in quantum optics, superconducting circuits, and ion traps have begun to test the boundaries of superposition. In 2010, researchers at Yale University created a superconducting circuit that behaved like an artificial atom, demonstrating superpositions of macroscopic currents. Similar experiments have pushed the boundary of quantum effects to ever larger systems, challenging the assumption that quantum behavior is confined to the microscopic realm. And yet, Schrödinger's original question remains: where does the quantum world end and the classical world begin? Is the boundary sharp or gradual? Is it determined by size, complexity, interaction, or something else entirely? What makes Schrödinger's cat so enduring is not just the image of a feline trapped in a quantum limbo, but the deeper mystery it represents, a mystery that cuts across physics, philosophy, and logic. It forces us to confront the limits of our understanding and the assumptions we make about reality, and it reminds us that, in the quantum world, even the act of observation is an act of creation. As quantum mechanics matured in the 20th century, one of its most persistent puzzles remained unsolved. Why do we not observe the strange behaviors predicted by quantum theory in our everyday lives? Superposition, entanglement, wave-particle duality, these features are confirmed in countless experiments at the microscopic scale. Yet in the macroscopic world of tables, trees, and cats, we see only definite outcomes. A ball is either on the floor or on the shelf. A coin is either heads or tails. There are no visible superpositions. Physicists needed an explanation, something that could bridge the quantum and classical realms without requiring a mysterious observer or invoking consciousness as a fundamental force. In the latter part of the 20th century, a promising concept began to take shape: quantum decoherence. To understand decoherence, we must begin with a basic idea from quantum theory. A quantum system, such as an electron, a photon, or an atom, can exist in a superposition of states. It evolves over time according to the Schrodinger equation, which describes how the probabilities of different outcomes change. If left completely isolated, a quantum system maintains this superposition indefinitely. But in the real world, no system is truly isolated. Every particle interacts, however slightly, with its environment. It might bump into stray photons, vibrate due to surrounding molecules, or become entangled with other particles. These interactions lead to what is called decoherence, the process by which quantum systems lose their coherence or capacity to maintain superposition due to environmental influence. The concept of decoherence was first explored in the 1970s and 80s, particularly through the work of German physicist H. Dieter Zeh, and later expanded by Polish-American physicist Wojciech Zurek. Their contributions helped formalize the mathematics and physical mechanisms behind decoherence, offering a powerful tool for interpreting quantum behavior. Imagine a quantum system in a superposition of two states, say, a particle being in two locations at once. As long as the system is perfectly isolated, it behaves like a single, coherent wave. But the moment it interacts with its environment, be it a measuring device, a thermal fluctuation, or even a stray atom, information about its state leaks into the surrounding world. These interactions entangle the system with its environment in complex ways. This entanglement doesn't destroy the wave function, but it does make the quantum superposition effectively unobservable. The different components of the wave function begin to interfere destructively, cancelling out their ability to produce measurable interference effects. In other words, the system still contains all possible states in theory, but from the perspective of an observer, only one outcome becomes apparent. This process happens extremely fast for macroscopic systems. The larger the object, the more particles it contains, and the more ways it can interact with its surroundings. For something like a dust particle in air, decoherence occurs in a fraction of a second. For larger objects like people or animals, the rate is so fast and the interactions so vast that quantum behavior becomes completely suppressed. Crucially, decoherence does not involve any collapse of the wave function in the traditional sense. The full wave function continues to exist, but its components no longer interfere with one another. In effect, the superposition is still there, but it becomes hidden from observation, washed out by noise and complexity. This idea helps resolve many of the puzzles raised by the Schrödinger's cat thought experiment. From the perspective of quantum theory, the cat may indeed begin in a superposition of alive and dead states. But the instant this superposition becomes entangled with the air molecules in the box, the atoms in the cat's body, and the thermal environment, decoherence kicks in. The alive and dead branches evolve independently, and any interference between them disappears. To an outside observer, only one outcome becomes accessible. The cat is seen as either alive or dead, not both. Decoherence thus provides a natural explanation for why quantum effects become invisible at larger scales. It also explains why we do not need a conscious observer to collapse the wave function. The environment itself, through constant interaction, effectively selects a definite outcome by suppressing interference between possibilities. However, decoherence alone does not solve all the mysteries of quantum mechanics. It explains how classical outcomes emerge, but it does not tell us why one particular outcome occurs instead of another. In a superposition of two states, decoherence explains why we cannot observe both at once, but it does not explain why we observe this one and not that one. That question, sometimes referred to as the problem of definite outcomes, remains a topic of debate. Still, decoherence offers a vital piece of the puzzle. It brings quantum mechanics into closer alignment with everyday experience, without requiring any new physics or speculative forces. It also plays a central role in emerging technologies, particularly quantum computing. In a quantum computer, information is stored in quantum bits, or qubits, which rely on superposition and entanglement to perform calculations that classical computers cannot. But qubits are fragile. They decohere rapidly when exposed to the environment, losing their quantum properties, and with them, the computational advantage. One of the great engineering challenges in quantum computing is to isolate qubits long enough to perform meaningful operations, while also finding ways to correct errors caused by inevitable decoherence. Researchers around the world, from institutions like IBM, Google, MIT, and the University of Oxford, are developing materials, cooling techniques, and error correction algorithms to mitigate decoherence. Some designs use superconducting circuits cooled to near absolute zero to reduce environmental interactions. Others use trapped ions or photonic systems to encode quantum information in ways that are more robust. Beyond computing, decoherence has implications for our understanding of the universe itself. In quantum cosmology, for instance, some theorists propose that the early universe began in a quantum superposition of all possible geometries and field configurations. Decoherence, triggered by interactions within the expanding cosmos, may have selected the classical spacetime we now observe. In this view, the large-scale structure of the universe, galaxies, stars, and planets, emerge through the same process that turns quantum uncertainty into classical definiteness. There are even experimental efforts underway to probe the boundaries of decoherence. Can we isolate a large molecule long enough to observe its quantum behavior? Can we delay decoherence to study how quantum to classical transitions occur? Researchers have created interference patterns with molecules consisting of hundreds of atoms, pushing the frontier of what can display quantum effects. As experimental techniques advance, we may gain deeper insights into the mechanisms and limits of decoherence. Another line of research involves so-called quantum Darwinism, a theory also developed by Wojciech Zurek. According to this idea, certain quantum states become favored because they are most robust under decoherence and most easily transmitted to the environment. These preferred states survive the decoherence process and become the classical reality we observe. Much like natural selection favors certain traits in biological evolution, quantum Darwinism suggests that the environment selectively amplifies certain outcomes over others. While still under investigation, quantum Darwinism offers a new way of thinking about how the classical world emerges, not as a direct result of measurement, but through the proliferation of information about particular states across the environment. In this framework, the environment acts as a kind of witness, constantly measuring quantum systems and spreading the results in a way that makes some outcomes more observable than others. Together, decoherence and quantum Darwinism bring us closer to understanding how the world we see arises from the quantum substrate beneath it. They allow us to describe how a definite reality emerges from a realm of probabilities and entanglements, without invoking hidden variables, alternate universes, or human consciousness as primary agents. Yet the mystery is not gone. Decoherence explains how the appearance of classical reality arises, but it still leaves open the deeper question of why particular outcomes occur. It also invites a more fundamental question. If information plays such a central role in shaping what we observe, could it be more than a useful concept? Could information be the very fabric of reality? As we have seen, quantum mechanics describes a world very different from the one we experience directly. Superpositions, entanglement, and decoherence all hint at a reality where probabilities and wave functions govern what is possible, until something is measured and a single outcome emerges. But that transition from possibility to actuality raises one of the most profound and unresolved questions in all of physics. What exactly is a measurement? And why does it appear to change the nature of reality? This is known as the measurement problem. It lies at the heart of quantum theory, and despite a century of research, no universally accepted answer has yet emerged. To appreciate the depth of this problem, consider a simple quantum system, an electron in a superposition of two energy states. As long as the system remains unmeasured, it evolves smoothly and deterministically, according to the Schrodinger equation. The electron is not in one state or the other. It is in a combination of both. described mathematically by its wave function. But when we measure the system, say, using a detector designed to register one energy level or the other, we always get a definite result. The detector shows either the lower state or the higher one. The wave function, which once described multiple possibilities, now describes only one. The other possibilities seem to vanish instantly. This abrupt transition from many outcomes to one is not predicted by the Schrodinger equation. It must be introduced as an additional postulate, often referred to as wave function collapse. But what exactly causes the collapse? Is it the physical interaction with the measuring device, the recording of the result, or is it the awareness of a conscious observer? This last possibility, that consciousness itself might be necessary for wave function collapse, has been seriously considered by several physicists, though it remains controversial. In the mid-20th century, Hungarian-American physicist Eugene Wigner explored this idea in a thought experiment known as Wigner's friend. Imagine that Wigner places his friend in a laboratory with a quantum system prepared in a superposition. Similar to the Schrodinger's cat scenario, the friend performs a measurement and sees a definite result. But from Wigner's point of view, outside the lab and unaware of the result, the entire lab, including the friend, is still in a superposition. Only when Wigner learns the outcome does he update his own description of the system. This leads to a paradox. If the wave function collapses when the friend observes the result, then collapse is independent of Wigner's knowledge. But if collapse only occurs when Wigner himself becomes aware, then the observer's consciousness plays a central role in determining reality. What, then, is an observer? Is Wigner's friend not an observer? Or must conscious awareness be nested in layers, each updating reality? Wigner's conclusion, though later revised, was that consciousness might be required to complete the measurement process. This view, while intriguing, raised more questions than it answered. What counts as conscious? Are animals observers? What about machines? And how does consciousness interact with physical systems? A similar idea was entertained by mathematician and physicist John von Neumann, who argued that the chain of measurement could be extended indefinitely, from particle to detector, detector to amplifier, amplifier to brain, and so on. Somewhere along this chain, the quantum system must become classical. But where? Von Neumann did not assign a specific location. Instead, he left open the possibility that consciousness marked the final step. Yet most physicists have been reluctant to place such weight on human awareness. Consciousness, after all, is not well understood. Introducing it as a fundamental component of physics feels unsatisfying to many researchers. It shifts the mystery rather than resolving it. In response, alternative interpretations of quantum mechanics have been proposed, each attempting to explain the measurement process without invoking consciousness and without breaking the mathematical formalism of the theory. One such interpretation is the decoherence framework we explored earlier. In this view, measurement is not a special act, but simply a type of interaction with the environment. The measuring device becomes entangled with the system, and decoherence rapidly suppresses interference between different outcomes. The system appears to collapse, but in fact, all outcomes continue to exist in a larger, entangled state. The observer sees only one outcome because they themselves become entangled with it. This leads naturally into the many worlds interpretation, which was introduced by Hugh Everett III in the 1950s. According to this view, every possible outcome of a quantum event actually occurs, but in separate, non-communicating branches of the universe. When you measure a quantum system, you do not collapse the wave function. Instead, you become entangled with one version of the outcome, while other versions of you become entangled with the others. In this framework, there is no special role for consciousness. Measurement is just a kind of interaction, governed by the same quantum laws as everything else. The universe keeps branching, and observers ride the branches. While this avoids the philosophical problems of collapse, it introduces a new challenge: the existence of a vast, possibly infinite number of parallel universes. Another approach is the so-called relational interpretation, proposed by Carlo Rovelli in the late 20th century. This view suggests that quantum states are not absolute, but relative. The state of a system is always defined with respect to an observer, whether that observer is a person, a measuring device, or another particle. There is no universal wave function, only relationships. Measurement, then, is not a physical transformation, but a change in the relational information between systems. While these interpretations differ, they all point to a central truth. The act of measurement cannot be fully separated from the observer. Whether the observer is a person, a machine, or an environment, their interaction with the system changes what is possible. The quantum world is not a detached objective stage, it is participatory. This idea has had wide-ranging implications. In quantum cryptography, for instance, the very act of eavesdropping on a message changes its content. This principle is used to create encryption systems that are, in theory, unbreakable. If someone tries to intercept a quantum key, their measurement alters the state of the system, revealing their presence. In quantum computing, measurement plays an even more critical role. Quantum algorithms often rely on maintaining superpositions across many qubits for as long as possible. A premature measurement, intentional or accidental, collapses the computation and ruins the result. Managing when and how measurement occurs is central to the operation of a quantum processor. Even in cosmology, the role of measurement has sparked debate. Some physicists have asked whether the early universe itself underwent a kind of quantum measurement. If the cosmos began as a quantum fluctuation, then what caused it to collapse into the classical universe we now observe? Was it the result of interactions within the expanding universe? Or does the very notion of measurement need to be redefined at the cosmic scale? As experimental techniques continue to improve, new tests are being designed to probe the boundaries of measurement. In some proposals, researchers hope to measure the gravitational field of a mass in quantum superposition, a test that would explore whether gravity itself can be in a quantum state. Others aim to test whether complex systems such as viruses or small biological structures can be placed in superposition and measured without collapse. The results of these experiments may help us better understand the role of the observer and whether the measurement problem is a true mystery or simply a misinterpretation of quantum language. What remains clear is that the measurement problem forces us to confront the limits of our definitions. What does it mean to observe? What qualifies as knowledge? And can reality exist independently of those who witness it? In classical physics, the fundamental elements of the universe have long been described in terms of matter and energy. Atoms, forces, and particles were once thought to be the most basic ingredients of nature. But as quantum theory has deepened, a new contender has entered the scene, one that may be even more fundamental than particles themselves: information. The notion that information might be the foundation of physical reality is not a metaphor or a philosophical curiosity. It emerges directly from the mathematics of quantum theory and has become a powerful framework in modern physics. It suggests that what we perceive as particles, fields, and forces may, at the most basic level, be manifestations of information processing, structured, encoded, and transformed in accordance with quantum rules. To understand this shift in thinking, we must begin with the field of information theory. In the mid-20th century, American mathematician Claude Shannon developed a mathematical framework to quantify and manage information. His work, published in the late 1940s, laid the foundation for digital communication. Shannon defined information not by its meaning, but by its structure, the amount of uncertainty it removes when a message is received. In this sense, information is a measure of surprise, of reduction in entropy. Shannon's theory revolutionized telecommunications, computer science, and cryptography, but its influence did not stop there. Physicists began to notice parallels between the way information behaves in digital systems and the way quantum systems evolve. Particularly in the quantum realm, where uncertainty, entanglement, and probabilities dominate, the language of information proved to be remarkably effective. One of the earliest bridges between physics and information came from physicist John Archibald Wheeler, who worked closely with both Niels Bohr and Albert Einstein. Wheeler is credited with the phrase "it from bit," meaning that every physical entity, the it, ultimately derives its existence from binary choices, the bit. In Wheeler's view, the universe does not consist of stuff, but of answers to yes or no questions. What exists is what can be distinguished, measured, and encoded. This concept gained further traction with the rise of quantum information theory, an interdisciplinary field that applies the tools of information theory to quantum systems. Unlike classical bits, which can be either 0 or 1, quantum bits, or qubits, can exist in a superposition of 0 and 1 simultaneously. This allows quantum systems to carry more complex forms of information than classical systems and to encode relationships between data points in ways that classical computers cannot match. Quantum information theory has uncovered some remarkable principles. For example, no-cloning theorem shows that it is impossible to create an identical copy of an unknown quantum state. This is a direct consequence of how information is structured in quantum systems and has deep implications for communication and computation. Similarly, quantum teleportation, which was first demonstrated experimentally in the 1990s, allows the transfer of quantum information between particles without physically moving them, using entanglement as the communication channel. But the implications go far beyond technology. Many physicists now believe that information plays a key role in the structure and behavior of the universe itself. In quantum mechanics, the state of a system is defined by a wave function, which contains all the information about that system. When we measure the system, we extract information from the wave function, effectively collapsing it into a definite state. This exchange of information is central to the evolution of quantum systems. The importance of information becomes even more striking when we consider black holes. In classical general relativity, black holes are defined by their mass, charge, and spin, but all other information about the matter that falls into them is thought to be lost. This led to the so-called black hole information paradox, first clearly formulated by Stephen Hawking in the 1970s. According to Hawking's calculations, black holes emit radiation and slowly evaporate over time. If information about what fell into a black hole is truly lost, then this process would violate a central principle of quantum mechanics. That information must be conserved. This paradox led to decades of debate. Was quantum theory incomplete? Did black holes somehow erase information forever? A major breakthrough came with the holographic principle, which suggests that all the information contained within a volume of space can be described by information encoded on its boundary. In other words, a three-dimensional region of space may be fully described by a two-dimensional surface. This radical idea emerged from the work of Gerard 't Hooft and Leonard Susskind in the 1990s and has since become a foundational concept in string theory and quantum gravity. The holographic principle implies that space itself may be emergent from information. If so, our familiar three-dimensional world could be analogous to a hologram with the real information encoded on a distant surface. This does not mean that our world is an illusion, but that the information needed to describe it may be stored differently than we imagine. In this context, the universe begins to resemble a vast computational system, one that stores, processes, and evolves information according to quantum laws. And this is not merely speculative. Modern physics increasingly describes physical systems in terms of entropic forces, quantum entropy, and information flows. Even space-time geometry, in some models, emerges from entanglement patterns in underlying quantum fields. One influential idea in this direction is entanglement entropy, which measures how much information is shared between different regions of a quantum system. Researchers have found that the structure of space-time in certain quantum gravity models can be reconstructed entirely from patterns of entanglement. This has led some to suggest that space itself is woven from information, much like fabric is woven from threads. The connection between information and reality is also central to the study of quantum error correction. In classical computing, errors can be detected and corrected by duplicating data and comparing results. In quantum systems, where cloning is forbidden, error correction must rely on more subtle techniques. Yet remarkably, the same mathematical structures used to protect quantum information also appear in models of quantum gravity. This suggests that the stability of space-time itself may depend on principles of quantum error correction. From this perspective, our universe may not only process information, it may be information. Particles are excitations of fields that encode data. Forces are rules for transforming information. Observables are measurements that extract bits of information from systems. And the laws of physics are algorithms that govern how information evolves. This approach offers new tools for solving old problems. In cosmology, the early universe can be modeled as a quantum information system with high entropy and low complexity. In particle physics, symmetries can be seen as constraints on how information transforms. In quantum computing, these ideas offer blueprints for building machines that use the universe's own rules to compute. Yet this shift also raises profound philosophical questions. If reality is ultimately made of information, then what is the role of the observer? Is consciousness another layer of information processing? Are laws of physics simply the rules of an immense computation? And could the entire cosmos be described as a quantum simulation running on a substrate of unknown design? These are not questions with simple answers, but they mark a turning point in the story of science. For centuries, we sought to understand the universe in terms of objects, substances, and forces. Now, we are beginning to see it in terms of logic, data, and structure. The shift from matter to information is more than a change in vocabulary. It is a transformation in how we understand existence itself. And if information truly lies at the root of physical law, then perhaps we are not just made of atoms and energy, but of bits and algorithms. This leads us toward an even more radical possibility that the universe, in all its quantum strangeness, might not be a random collection of particles, but a vast, ordered system of encoded relationships, a computational fabric where observation, causality, and even consciousness arise from quantum information. In the world of classical physics, objects are distinct, separable, and influenced only by their immediate surroundings. A ball in motion, a planet in orbit, or a pendulum swinging through the air, each obeys local laws. The force that affects them must be physically nearby. But in the quantum realm, this intuition breaks down. Particles can become mysteriously linked in such a way that the state of one instantly affects the state of another, no matter how far apart they are. This is not a metaphor. It is a measurable, repeatable phenomenon known as quantum entanglement, and it challenges our deepest assumptions about space, causality, and the nature of reality. Entanglement first emerged as a feature of quantum theory in the early 20th century. When two particles interact in a particular way, their quantum states can become correlated. After this interaction, measuring one particle's properties allows you to predict the outcome of measuring the other, even if the two are separated by light years. The twist is that until measured, neither particle has definite properties. They exist in a superposition of possibilities. Yet once a measurement is made on one particle, the other instantly assumes a correlated state. This defies classical expectations. In Newtonian physics, information cannot travel faster than light. Causes and effects must occur in sequence, and signals must obey the speed limit of the universe. But entanglement seems to operate outside this framework. Albert Einstein famously described it as spooky action at a distance, a phrase that captured both his skepticism and the unsettling nature of the effect. Einstein was not alone in his concern. In 1935, he co-authored a paper with Boris Podolsky and Nathan Rosen presenting what is now known as the EPR paradox. The paper argued that quantum mechanics, as it stood, could not be a complete description of reality. If measuring one particle instantly determined the state of another distant particle, then either information was traveling faster than light, a violation of relativity, or the particles had hidden properties that determined their behavior in advance. Einstein and his colleagues favored the latter explanation. They proposed that quantum mechanics was incomplete and that some deeper layer of physical reality, governed by what they called hidden variables, would eventually restore determinism and locality. For decades, this debate remained unresolved. Quantum mechanics continued to predict entanglement, but no experiment could definitively show whether hidden variables were at play. That changed in the 1960s when Irish physicist John Bell formulated a mathematical framework that could test the issue directly. Bell derived a set of inequalities, now known as Bell's inequalities, that must be satisfied by any theory based on local hidden variables. Quantum mechanics, by contrast, predicts that these inequalities can be violated under certain conditions. This was a crucial turning point. Bell's work transformed a philosophical debate into an empirical question. If experiments could demonstrate violations of Bell's inequalities, then local hidden variable theories would be ruled out. The universe, it seemed, would have to be non-local, or at least far stranger than Einstein had imagined. The first experimental tests came in the 1970s, but it was not until the early 1980s that a definitive result was achieved. At the Institut d'Optique in France, physicist Alain Aspect and his team conducted a series of experiments using entangled photons. They measured the polarization of each photon in pairs, varying the measurement settings randomly and rapidly. The results showed clear violations of Bell's inequalities, confirming the predictions of quantum mechanics and casting doubt on local realism. Over the following decades, similar experiments were repeated and refined. Loopholes were closed, detectors were improved. In 2015, a trio of landmark experiments in the Netherlands, the United States, and Austria performed what are known as loophole-free Bell tests. These experiments addressed all known limitations, including the possibility that detector inefficiencies or communication between devices could have influenced the results. The outcome was clear and consistent. Bell's inequalities were violated. Quantum entanglement was real, and any attempt to explain it using local hidden variables was incompatible with the data. What does this mean for our understanding of reality? First, it tells us that non-local correlations exist in nature. When two entangled particles are measured, their outcomes are connected in a way that cannot be explained by any signal traveling between them, at least not one that respects the speed of light. This does not allow for faster-than-light communication, but it does suggest that the universe allows connections that are not mediated by local interactions. Second, it reinforces the idea that quantum states are relational and contextual. The result of measuring one particle depends not only on its own properties, but also on how and when the other particle is measured. This interdependence undermines the classical idea of independent, self-contained systems. Third, it strengthens the role of information in quantum theory. Entangled particles are not individual carriers of independent facts. Instead, the information they carry is distributed across the entire system. You cannot assign complete information to either particle alone, only to the system as a whole. Some interpretations of quantum mechanics embrace this non-locality as a fundamental feature. In Bohmian mechanics, for example, particles have definite positions, guided by a quantum wave that spans space. This wave contains pilot information that instantly coordinates behavior across distances. Though Bohm's theory restores determinism, it does so at the cost of introducing non-local hidden variables. Other approaches, like the many worlds interpretation, explain entanglement without invoking non-local signals. In this view, when a measurement occurs, the universe splits into branches where each outcome is realized. The correlations arise because each version of the observer experiences a consistent result within their own branch. No signal is needed because all outcomes exist in parallel. Still, the consensus is that entanglement is a uniquely quantum phenomenon with no classical analog. Its effects have been demonstrated not just in photons and electrons, but in atoms, ions, superconducting circuits, and even small molecules. Researchers continue to push the boundaries, exploring whether larger and more complex systems can exhibit entanglement over greater distances. Beyond theory, entanglement has become a practical tool in modern technology. In quantum cryptography, it enables secure communication by detecting any attempt to intercept or tamper with a message. In quantum teleportation, it allows the transfer of quantum states from one location to another without moving the physical particle itself. And in quantum computing, entanglement provides the key to parallel processing and exponential speedups over classical systems. Entanglement also plays a role in quantum networks, an emerging field that aims to connect quantum devices over long distances. These networks could form the backbone of a future quantum internet, capable of sharing entangled states between nodes and performing distributed quantum computations. Governments and research institutions around the world are investing in this technology, hoping to unlock new capabilities in sensing, communication, and computation. Yet despite its utility, entanglement remains deeply mysterious. What kind of reality permits such non-local connections? Are particles truly separated in space, or are they part of a deeper unity that transcends location? Is space itself a derived concept, emerging from underlying informational or relational structures? Some theorists believe that entanglement may hold the key to understanding space-time itself. In recent years, proposals from quantum gravity and string theory suggest that the geometry of space-time could emerge from patterns of entanglement in more fundamental quantum systems. According to this view, space is not a fixed background, but a consequence of how information is shared between quantum subsystems. If this is true, then entanglement is not just a curious feature of particles. It is the fabric from which reality is woven. Particles are entangled because the universe itself is entangled, and the space between them exists only because their quantum correlations allow it. This vision remains speculative, but it is supported by growing evidence from theoretical models and numerical simulations. It suggests that our classical intuition about separability, distance, and causality may be illusions born from a deeper, interconnected foundation. Quantum entanglement, once dismissed as an oddity, now stands at the center of physics. It reveals a universe that is non-local, holistic, and governed by correlations that defy space. It shows that information is not confined, but shared, and it invites us to reconsider what it means for something to be separate at all. For centuries, space has been treated as the silent stage upon which all of physics unfolds. It is where objects exist, where distances can be measured, and where the laws of nature operate. Time, meanwhile, marches alongside it, a steady tick to which all matter and energy must respond. Together, space and time have defined the playing field of classical and modern physics alike. But in recent decades, an astonishing idea has taken root in theoretical physics: that space itself, and perhaps even time, might not be fundamental at all. Instead, our seemingly three-dimensional universe might be a projection, a kind of hologram, generated by information encoded on a lower dimensional boundary. This is the essence of the holographic principle, a concept that has redefined the frontier of modern theoretical physics. It suggests that all of the information contained in a volume of space can be fully described by information that resides on the surface surrounding that volume. This idea, inspired by deep puzzles in black hole physics, proposes that the universe may be fundamentally two-dimensional, with the third dimension of space emerging from more basic informational structures. The story begins, as many radical developments do, with a paradox. In the early 1970s, Jacob Bekenstein, a graduate student at Princeton University, made a surprising proposal. He suggested that black holes, contrary to earlier assumptions, possess entropy. Entropy is a measure of disorder, or more precisely, of how much information is hidden within a system's microscopic states. If black holes have entropy, then they must also have a temperature and radiate energy. This ran counter to the long-standing view that nothing escapes a black hole, not light, not heat, not information. Stephen Hawking, working independently at the University of Cambridge, soon took this idea further. Through a quantum mechanical analysis of fields near the event horizon of a black hole, he demonstrated that black holes do indeed emit radiation. This emission, now called Hawking radiation, arises from quantum fluctuations near the event horizon that cause particle-antiparticle pairs to appear. One of these particles can fall into the black hole while the other escapes, making the black hole appear to radiate. Hawking's calculation revealed that black holes slowly evaporate over time, losing mass as they emit radiation. But this led to a new problem: the black hole information paradox. If a black hole eventually evaporates completely, what happens to the information about the matter that fell into it? Quantum mechanics demands that information is preserved in physical processes, but black hole evaporation, according to classical understanding, seemed to destroy it. This tension between quantum mechanics and general relativity prompted intense investigation. In 1993, Dutch physicist Gerard 't Hooft made a bold suggestion. He proposed that all of the information contained in a region of space could be encoded on its boundary, in a way similar to how a hologram encodes three-dimensional images on a two-dimensional surface. A hologram is a flat sheet that stores information about a full three-dimensional image using interference patterns. When illuminated properly, the image appears three-dimensional, even though it originates from a flat source. Inspired by this analogy, 't Hooft speculated that a similar principle might apply to the universe itself. His idea was refined and expanded by American physicist Leonard Susskind, who named it the holographic principle. According to Susskind, the information content of any spatial region is not proportional to its volume, as one might expect, but to its surface area. The number of bits needed to describe a physical system is determined not by how much space it fills, but by the area of its boundary, measured in fundamental units, known as Planck areas. This was a radical shift. In everyday experience, we expect the amount of information or complexity in a system to grow with its size. A larger room contains more air molecules, more possibilities, and therefore more information. But the holographic principle asserts that all of this can be encoded at the boundary, much like the pixels on a digital screen can produce a vast and immersive virtual environment. Still, bold as it was, the holographic principle remained speculative until it found a precise mathematical expression. That breakthrough came in the late 1990s through the work of Argentine physicist Juan Maldacena, who formulated a specific model in which the holographic principle could be tested rigorously. His model, now known as the ADS-CFT correspondence, describes a duality between two very different kinds of physical theories. On one side of this duality is a conformal field theory, CFT, defined on the boundary of a space. This theory contains no gravity and exists in fewer dimensions. On the other side is a theory of quantum gravity operating in the full, higher dimensional space known as anti-de Sitter space, ADS. Maldacena showed that these two theories, though seemingly unrelated, are mathematically equivalent. Every physical process in the bulk gravitational theory has a corresponding process in the boundary field theory. This discovery was revolutionary. It provided the first concrete realization of the holographic principle and offered physicists a new way to understand quantum gravity. Instead of trying to quantize space-time directly, they could study its lower-dimensional holographic dual, where gravity does not exist and calculations are more tractable. The ADS-CFT correspondence is highly specific. It applies to a universe with constant negative curvature, which is not the universe we live in. Our observable cosmos appears to be nearly flat or slightly positively curved. Still, the correspondence has become a powerful tool for exploring broader principles, and it has inspired a wealth of research into how space, time, and gravity might emerge from more fundamental, non-spatial theories. One of the most intriguing insights from this work is that entanglement may play a critical role in the emergence of space-time geometry. As mentioned in the previous section, patterns of quantum entanglement between parts of a system determine how information is shared. In holographic models, researchers have found that the connectivity of space, its curvature and topology, can be reconstructed from the entanglement structure of the boundary theory. If two regions are highly entangled, they are close in the geometric sense, even if they are distant in the coordinate sense. This leads to a powerful conclusion. Space may not be a static backdrop, but a dynamic structure arising from the flow of information. The very shape of space could be a map of entanglement. The fabric of the universe, in this view, is not made of particles or fields, but of relationships, encoded patterns of information distributed across a boundary surface. If this is correct, then the three-dimensional world we experience is not fundamental but emergent. It arises from something more abstract, possibly a two-dimensional field theory that contains no gravity, no space, and no time as we know them. In this framework, the concept of location becomes secondary to the concept of correlation. Events are not defined by where they are, but by how they are entangled. Such ideas, while difficult to test directly, resonate with developments in quantum computing, information theory, and cosmology. They hint at a universe that is deeply computational, where geometry and physics arise from deeper informational rules. The holographic principle invites us to consider that our experience of space is a kind of illusion, useful, consistent, but not fundamental. This perspective aligns intriguingly with the simulation hypothesis. If the universe is a holographic projection of encoded information, then it already behaves like a form of simulation, one that translates abstract data into physical experience. The rules of physics, in this view, are not the source of reality, but its consequence, emergent behaviors arising from underlying informational constraints. What if reality is not a continuum but a computation? What if the universe, down to its deepest layer, operates not as a smooth fabric of space and time, but as a discrete system governed by logic, algorithms, and data structures? This is the central question of digital physics, an emerging field of inquiry that proposes the universe itself is fundamentally computable. Digital physics is not simply a metaphor, nor is it about visualizing the universe as a vast spreadsheet or a software simulation in the conventional sense. It is the rigorous attempt to model the workings of physical reality as a computational process, one that may be running on some substrate that we do not yet understand. The idea is radical, but it arises naturally when we consider how successful computational models have become at describing complex systems and predicting physical behavior. To trace the origins of this idea, we return to the mid-20th century when digital computation first came into existence. The work of Alan Turing, who formalized the concept of the Turing machine, introduced the notion of a universal computational model. A Turing machine is a hypothetical device that manipulates symbols on a strip of tape according to a set of rules. Despite its simplicity, it can simulate any computation that can be performed by a digital computer. Turing's work, combined with developments in algorithm theory and logic, laid the foundation for computer science. But it also had unexpected consequences for physics. If physical systems could be simulated by computers, then perhaps the systems themselves were computational. This idea gained traction in the following decades. One of the earliest and most explicit proposals came from German engineer Konrad Zuse, who is best known for building the first programmable computer in the 1940s. In the 1960s, Zuse proposed that the universe might be running on a cellular automaton, a grid-like structure where each cell changes its state according to fixed rules based on the states of its neighbors. He called this idea rechnender Raum, or computing space. Zuse imagined that space itself could be broken down into discrete units, each updating at each tick of an underlying clock. The behavior of matter, energy, and even quantum phenomena would emerge from the local interactions of these computational cells. At the time, Zuse's idea was speculative and lacked mathematical rigor, but it would prove influential. In the 1980s and beyond, American physicist Edward Fredkin expanded on Zuse's ideas. Fredkin proposed that the universe is a kind of digital machine where the fundamental components are bits of information, not particles or fields. In Fredkin's digital philosophy, space and time are not continuous, but quantized. Every event, every movement, every force is the outcome of logical operations executed on a vast informational network. Fredkin went further, suggesting that even conservation laws, such as energy and momentum, could arise from the invariance of computational rules over time. In this view, the universe is not running on a computer, it is a computer. The behavior of everything we see is the result of informational processes governed by digital laws. Meanwhile, mathematician Stephen Wolfram developed an approach that emphasized simplicity and emergence. In his work with cellular automata, Wolfram discovered that extremely simple rules can give rise to incredibly complex and unpredictable behavior. His Rule 110, a one-dimensional cellular automaton with only 2 possible states per cell and very basic updating rules, was shown to be Turing complete, capable of performing any computation that a digital computer can execute. Wolfram's later work, compiled in A New Kind of Science, argued that the richness of the universe could emerge from the iteration of simple computational rules. He proposed that the universe itself might be based on a network-like structure, evolving over discrete steps, and that physics as we know it is the large-scale behavior of this deeper computational substrate. One of the key concepts in Wolfram's approach is that complexity does not require complex laws. Instead, patterns and behaviors we associate with intelligence, randomness, or structure can arise naturally from repetition, iteration, and feedback. This insight has influenced not only theoretical physics, but also artificial life, complexity science, and computational biology. Still, digital physics is not without its challenges. One of the primary difficulties lies in reconciling the discreteness of computation with the apparent continuity of space and time. Traditional physics relies on smooth differential equations, such as those found in general relativity or quantum field theory. If the universe is fundamentally digital, why does it appear continuous? Proponents of digital physics argue that continuity may be an illusion, a large-scale approximation of countless discrete events. Just as a digital image can appear smooth from a distance despite being composed of pixels, the fabric of space-time may only seem continuous because our observational tools are limited in resolution. Indeed, some theoretical efforts have attempted to detect this discreteness directly. Certain models of quantum gravity, such as loop quantum gravity, suggest that space is quantized into indivisible units. These models propose that areas and volumes come in discrete chunks, and that time itself might progress in minimal steps. Although experimental confirmation remains elusive, such theories offer a potential bridge between the smooth mathematics of relativity and the quantized world of quantum mechanics. Other researchers have explored the idea that the laws of physics may be the output of computational processes. British physicist Julian Barber has proposed models where time does not exist as a flowing dimension, but as a series of discrete snapshots, each containing a complete configuration of the universe. According to this view, change and motion are illusions created by the ordering of these configurations. More recently, researchers in quantum information theory have found further support for digital perspectives. The finiteness of quantum information, demonstrated by the no-cloning theorem and limits on information transmission, suggests that the universe may not contain infinite detail. Quantum mechanics imposes fundamental bounds on how much information can be stored and transferred, supporting the idea of a finite, computable reality. In practice, physics has embraced computation as a tool, even if it has not fully accepted it as a foundation. Simulations are now central to cosmology, climate science, particle physics, and materials research. Whether modeling the collision of galaxies or the behavior of quarks, physicists routinely use digital machines to approximate the dynamics of nature, but the hypothesis of digital physics turns this process inside out. It suggests that the reason computers are so good at modeling the universe is not merely a matter of approximation, it is a reflection of how the universe actually works. Our best simulations are not just analogies, they are imitations of the real processes that shape the cosmos. Of course, many questions remain. What substrate would a digital universe run on? Is there a master algorithm? And if so, what writes it? Are there fundamental bits of space and time? And can we ever observe them directly? These are open questions, but they are being taken increasingly seriously. As theoretical and computational tools grow more powerful, physicists are exploring new ways to test the assumptions of digital physics. Experiments are being designed to look for evidence of discreteness in space, time, and energy spectra. Observations of the cosmic microwave background, ultra-high energy cosmic rays, and gravitational waves may one day reveal the granularity of space itself. Digital physics does not yet offer a complete theory of everything, but it represents a powerful paradigm, a way to think about the universe not as a passive backdrop, but as an active system of computation. If true, it would mean that everything we see, every law we follow, and every event we witness is part of a vast, evolving program. And that brings us to a critical question. If the universe is a computation, can it be simulated? Can we recreate its behavior on a digital machine? More provocatively, is it already being simulated? Could our reality itself be the output of some cosmic computation, one not of our making? The idea that complex structures can emerge from simple rules is one of the most powerful and counterintuitive concepts in science. In the context of digital physics, this idea becomes especially important. If the universe is a kind of computation, if it operates according to discrete, rule-based processes, then we should expect to find systems that, while based on simple foundations, can evolve into extraordinarily rich and unpredictable forms. One of the most illuminating examples of this principle comes not from quantum physics or cosmology, but from a deceptively simple computer program known as the game of life. Invented in the late 1960s by British mathematician John Horton Conway, the game of life is a type of cellular automaton, a system in which space is divided into discrete cells, each of which can be in one of a finite number of states. Time progresses in steps, and at each step, every cell updates its state based on a set of local rules that take into account the states of its neighboring cells. Despite this simplicity, cellular automata can exhibit extraordinarily complex and even lifelike behavior. The game of life takes place on a two-dimensional grid where each cell can be either alive or dead. The state of each cell in the next generation is determined by a fixed set of rules. A living cell with fewer than 2 living neighbors dies due to underpopulation. A living cell with 2 or 3 living neighbors survives to the next generation. A living cell with more than 3 neighbors dies due to overcrowding. A dead cell with exactly 3 living neighbors becomes alive, as if by reproduction. These rules are applied simultaneously to all cells on the grid. With each new step, called a generation, the entire configuration of the system changes. What makes the game of life so remarkable is what emerges from these simple instructions. Patterns appear that move, grow, oscillate, and replicate. Some remain static, others evolve unpredictably. There are gliders, structures that appear to travel across the grid. There are guns, patterns that periodically shoot gliders into space. There are even self-replicating patterns, capable of building copies of themselves. At first glance, these behaviors may seem incidental or toy-like, but the implications run deep. Conway's game of life is Turing complete, meaning that it can, in principle, perform any computation that a standard digital computer can execute. Given the right initial configuration, the game of life can simulate any logical process, including mathematical operations, decision-making systems, and even other cellular automata. It can simulate itself. This is a profound realization. Out of a grid of binary states and a handful of rules, one can produce systems as powerful as any known computational device. Complexity, intelligence, and structure are not limited to complicated starting points. They can emerge from simplicity, given time, space, and rules. The game of life and its relatives have become a fertile testing ground for ideas in complexity science, artificial life, and computational theory. Researchers have used cellular automata to model fluid flow, biological growth, neural networks, and even social behavior. In many of these models, surprising levels of order and complexity arise spontaneously without the need for central control or design. This phenomenon, called emergence, is key to understanding how large-scale systems can be governed by low-level interactions. In biological organisms, for instance, cells follow local biochemical rules, yet form tissues, organs, and consciousness. In weather systems, air molecules obey physical laws, yet give rise to storms and climate. In economies, individuals make choices, yet markets and patterns develop that no single agent controls. Cellular automata help us see how these principles might be abstracted and applied more generally. They invite the question, could the universe itself be an emergent system evolving according to simple rules encoded in the fabric of space and time? Physicist Stephen Wolfram, mentioned in the previous section, believes the answer may be yes. His extensive study of cellular automata led him to propose that the richness of the physical world can emerge from extremely basic computational rules. In his framework, the universe is not fundamentally a collection of particles or waves, but a network of updating elements following discrete rules, a kind of computational graph whose connections shift with each tick of the cosmic clock. Wolfram's work suggests that physics may not be about differential equations, but about rule systems. Instead of treating space and time as continuous dimensions, he imagines them as discrete steps and connections, closer in spirit to the game of life than to Einstein's smooth geometries. This vision, while controversial, has profound implications for how we understand both reality and simulation. If simple rules can give rise to the kind of complexity we observe in cellular automata, then perhaps the laws of physics are themselves rules in a broader computation. And if those rules can be discovered and encoded, then in principle, one could simulate a universe. Indeed, scientists and engineers already use rule-based simulations to study physical systems. Weather models break the atmosphere into grids and apply equations to each cell. Astrophysical simulations track particles and fields using discrete steps. These tools are approximate, of course, but they demonstrate how local rules applied to discrete units can model global phenomena. In recent years, physicists have developed quantum cellular automata, models that apply quantum rules to systems similar in spirit to Conway's grid. In these models, cells can be in superpositions, entangled with others, and governed by unitary evolution. Quantum cellular automata are still a developing field, but they offer a path towards simulating quantum systems using rule-based architectures. One notable example is the quantum lattice gas automaton, which simulates the behavior of quantum fluids using local update rules. These models capture interference, superposition, and entanglement, while being defined entirely in discrete terms. Some researchers have even proposed that quantum field theories, the mathematical backbone of modern particle physics, might be approximated by carefully designed automata. The success of these approaches strengthens the idea that computation and simulation are not mere analogies, but reflections of physical structure. If the universe behaves like a cellular automaton, then running a simulation of such a system is not an imitation, it is an instantiation. It becomes difficult to distinguish between real and simulated at the level of fundamental behavior. This leads to a provocative idea. If complexity, structure, and even life can emerge from simple computational rules, then perhaps our own reality is the product of such rules. The game of life, in this sense, is not just a curiosity, it is a demonstration that universes with complex dynamics can arise from minimal assumptions. But this also raises deeper philosophical and scientific questions. If our universe is governed by computational rules, can we ever know the rules completely? Are they fixed or evolving? Could they have been chosen? Or are they inevitable? Some researchers suggest that universes like ours might arise frequently in a landscape of all possible rule sets. In this landscape, most rules produce chaos or emptiness. Only a few produce stable, structured, and complex systems, capable of observers, thoughts, and reflections. In that sense, our universe may be rare, but not unique. And if such rule sets can be known, they can also be replicated. With the growth of computational power and quantum simulation technologies, we are approaching the ability to create artificial environments governed by rule-based physics. These simulations may one day contain autonomous agents, adaptive behaviors, and emergent complexities that mirror our own. When that happens, the distinction between simulated and natural worlds becomes a matter of structure, not of status. As we step into that possibility, the boundaries between mathematics, physics, and metaphysics blur. Cellular automata, like the game of life, show us that with simple rules and enough iterations, patterns of astonishing complexity and diversity can emerge, patterns that resemble life, evolution, and intelligence. If these features can emerge from code, then the notion that our own universe is, at its core, a simulation governed by code becomes less far-fetched. As abstract and philosophical as the idea of a simulated universe may sound, the concept of simulation is deeply embedded in the practice of modern science. Physicists, chemists, biologists, and engineers rely on simulations every day to model complex systems, predict outcomes, and explore environments that would be impossible, or at least impractical, to recreate physically. Simulations have become more than tools. They are extensions of scientific reasoning, capable of revealing truths about the universe that would otherwise remain inaccessible. These simulations are not mere visualizations. They are computational experiments that mimic the behavior of real-world systems using mathematical models and physical laws. In doing so, they bring together the theoretical and the empirical, allowing scientists to explore what-if scenarios that stretch from the microscopic to the cosmic. One of the most profound uses of simulation lies in cosmology, the study of the origin and evolution of the universe. Since the late 20th century, scientists have built computer models to simulate the formation of galaxies, the distribution of dark matter, and the dynamics of cosmic expansion. These simulations start with simple initial conditions, such as density fluctuations in the early universe, and evolve them forward in time using the known laws of gravity, thermodynamics, and quantum mechanics. A prominent example is the Illustris project, a large-scale cosmological simulation developed by researchers from institutions such as MIT, the Max Planck Institute, and Harvard. This simulation tracks billions of particles representing dark matter, gas, and stars, allowing scientists to watch virtual galaxies form and evolve across billions of years. When compared with observational data from telescopes, the results of these simulations often align remarkably well, reinforcing the idea that they capture essential features of reality. Even more detailed is the Eagle simulation, evolution and assembly of galaxies and their environments, which adds layers of astrophysical processes like supernova feedback, black hole growth, and chemical enrichment. These simulations not only match observed galaxy distributions, but also help explain subtle features of galactic structure, such as rotation curves and star formation rates. Simulations have also transformed particle physics, where direct observation often hits the limits of scale and energy. Experiments like those conducted at CERN's Large Hadron Collider involve particles moving at speeds close to that of light and colliding at energies too extreme for any intuitive understanding. To analyze these events, researchers use simulations based on the standard model of particle physics to predict possible outcomes and compare them with experimental results. Simulations allow researchers to test hypothetical particles, forces, and interactions that may not yet be accessible through direct experimentation. By adjusting parameters within these digital frameworks, scientists can explore extensions to the standard model, such as supersymmetry or extra dimensions, guiding the search for new physics. In the realm of quantum mechanics, simulations are especially valuable because the behavior of quantum systems can become overwhelmingly complex. The state of a system with even a modest number of entangled particles can require vast computational resources to represent and manipulate. Classical computers quickly reach their limits, which has led to the development of specialized methods, such as quantum Monte Carlo simulations and density functional theory, to approximate the properties of quantum systems. These simulations play a vital role in materials science, where they are used to design new compounds with specific electronic, thermal, or magnetic properties. By modeling the quantum interactions between atoms and electrons, scientists can predict how a material will behave under different conditions without having to synthesize it first. This accelerates the discovery of high-performance alloys, superconductors, and nanomaterials. Perhaps nowhere is the simulation concept more pervasive than in climate science, where global models integrate vast datasets from the oceans, atmosphere, ice sheets, and biosphere. These simulations are among the most complex ever created, often requiring the combined power of supercomputers across continents. They allow researchers to forecast long-term climate changes, understand feedback loops, and evaluate the potential impact of human activity on Earth's future. But simulations are not confined to scientific laboratories. They have also taken root in engineering, economics, medicine, and even urban planning. Engineers use finite element analysis to simulate stress and deformation in bridges and buildings. Economists build agent-based models to explore market behavior. Neuroscientists simulate brain networks to investigate cognition and consciousness. In each case, simulations allow for exploration beyond the reach of direct manipulation or observation. The ability to simulate also extends to entertainment and virtual environments. Video game engines, augmented reality, and virtual reality platforms create immersive digital spaces governed by physics engines that mimic real-world motion, lighting, and sound. Though designed primarily for interaction and visual appeal, these platforms demonstrate how convincing and coherent a simulated world can feel when it follows internally consistent rules. As simulation fidelity increases, so too does the blurring of lines between real and virtual. Flight simulators now train pilots with such accuracy that they are certified as equivalent to real flight hours. Virtual surgery platforms allow medical students to practice complex procedures with tactile feedback and real-time diagnostics. Autonomous vehicles rely on simulated driving environments to learn how to navigate roads before ever touching pavement. These real-world applications of simulation raise a striking question. If we can create simulated environments that behave with convincing realism, then how would an inhabitant of such a simulation know it was inside one? From inside the system, all measurable phenomena would follow the programmed rules. Gravity would act as expected, light would reflect predictably, chemistry would proceed in stable, testable ways. This question is not merely academic. In the early 21st century, philosopher Nick Bostrom formalized an argument suggesting that if advanced civilizations develop the ability to run realistic ancestor simulations, detailed recreations of their evolutionary or cultural past, then the number of simulated beings could vastly exceed the number of original biological beings. If such simulations are possible and common, then it becomes statistically more likely that any given conscious observer is within a simulation rather than the base reality. While Bostrom's argument will be addressed in depth in a later section, Its philosophical core connects directly to the rise of simulations in practice. The better we become at creating them, the more plausible it becomes that others, perhaps far more advanced than we are, could have done so already. If the universe we experience can be accurately simulated by machines of our own making, the difference between simulation and physicality may become one of perspective rather than substance. This possibility pushes against the boundaries of empirical science, but it also motivates new research. Physicists have begun to ask whether certain features of the universe might betray signs of simulation. Could anomalies in cosmic background radiation, quantization of space-time, or unexplained limits in particle energies reflect the underlying resolution of a digital universe? Are there statistical signatures, glitches in the matrix, that we might one day detect? Although these questions remain speculative, they are no longer dismissed outright. As simulations become more powerful and more integral to the scientific process, the idea that our reality might be computational gains conceptual credibility. Already, researchers working at the intersection of physics and computer science speak of information-based ontologies, where the fundamental units of existence are not particles or forces, but bits of data and rules of transformation. Simulations also force us to reconsider traditional boundaries between the observer and the observed. In classical science, the observer is outside the system, gathering data and forming conclusions. But in a simulation, the observer may be part of the system itself. The act of simulation becomes self-referential, a world aware of its own structure through entities embedded within it. This brings us full circle to the question that underlies much of this documentary. If simulated realities are indistinguishable from physical ones at the experiential level, and if they are increasingly easy to construct, then what assumptions can we safely make about the world we inhabit? In the early years of the 21st century, a thought-provoking and meticulously reasoned philosophical idea captured the attention of scientists, futurists, and technologists alike. It did not originate in a physics laboratory or a computer science department, but emerged instead from the field of philosophy, specifically from the mind of Swedish philosopher Nick Bostrom, a professor at the University of Oxford. His work, known as the simulation argument, does not claim that we are definitely living in a simulated reality. Rather, it presents a logically structured trilemma. At least one of three possibilities must be true, and if the first two are false, then the third, namely, that we are almost certainly living in a simulation, becomes extremely difficult to reject. The argument is not a whimsical speculation. It is a probabilistic reasoning exercise rooted in technological trends, philosophical logic, and an extrapolation of future capabilities. Its strength lies in its simplicity, its breadth, and the fact that it requires very few assumptions beyond what is already plausible given the current trajectory of computational technologies. At the core of Bostrom's simulation argument is a simple idea. If technologically advanced civilizations ever develop the capability to run realistic simulations of their ancestors, and if they choose to run many such simulations, then the number of simulated minds could vastly exceed the number of original biological minds. In such a scenario, the odds that any particular conscious experience belongs to a biological human rather than a simulated one would become vanishingly small. To understand the structure of the argument, we must break it down into its three central propositions. Bostrom's trilemma is framed as follows. First, almost all civilizations at our level of technological development go extinct before becoming capable of creating such ancestor simulations. This is a kind of great filter hypothesis, suggesting that technological civilizations tend to destroy themselves, perhaps through warfare, ecological collapse, or uncontrolled artificial intelligence, before they reach a level where such simulations are possible. Second, even if civilizations survive and develop the technical ability to run realistic ancestor simulations, almost none of them are interested in doing so. This could be due to ethical constraints, cultural disinterest, or the sheer computational cost involved. Perhaps advanced societies consider it immoral to simulate conscious beings, or perhaps they turn inward, focusing on other forms of knowledge or experience. Third, if the first two propositions are false, if some civilizations do survive and choose to run simulations, then the number of simulated minds would, in all likelihood, vastly outnumber the original biological ones. In that case, it becomes statistically more probable that we ourselves are among the simulated minds rather than the originals. Bostrom emphasizes that we cannot confidently determine which of these three options is correct, but he argues that they are logically exhaustive. If one rejects the first and second propositions, the third follows almost inevitably. This trilemma reframes the simulation hypothesis from an abstract possibility to a question of probability and demographics. It does not require proof that a simulation is currently running. It only asks us to consider what would happen if civilizations were to develop the ability to create such simulations and were motivated to do so. Critically, Bostrom's argument sidesteps many of the traditional metaphysical debates about mind and machine. It does not depend on whether consciousness can be fully emulated by digital processes, though that is an important underlying assumption. Instead, it focuses on the relative abundance of conscious entities across simulated and non-simulated realities. If the ratio of simulated to real experiences is extremely high, then it becomes reasonable, based on pure statistics, to suspect that we might be among the former. This probabilistic approach has drawn both praise and criticism. Supporters find it compelling because it places the burden of proof on those who claim we are not in a simulation. After all, if the capacity for simulation exists and is used, then being a simulated consciousness becomes the default expectation. Skeptics, on the other hand, argue that the reasoning depends too heavily on assumptions about future technologies and motivations. Perhaps simulation is far more difficult than we currently imagine. Perhaps consciousness cannot be replicated in silicon. Or perhaps the ethical standards of advanced civilizations render such simulations socially or morally unacceptable. Others raise questions about the empirical testability of the simulation hypothesis. If it cannot be tested or falsified, they argue, then it may not qualify as a scientific hypothesis at all. It might belong more to the realm of metaphysics than physics. Yet Bostrom's formulation carefully avoids claiming that we are in a simulation. He does not assert this as fact, but instead presents the conditions under which the likelihood would be high. This subtlety is important. The simulation argument is not a theory of physics, nor is it a belief system. It is a challenge to our intuitions about identity, technology, and the future of intelligence. Despite its philosophical roots, the simulation argument has had ripple effects far beyond academia. Influential figures in technology and science, including Elon Musk, Neil deGrasse Tyson, and others, have publicly commented on the likelihood that we are living in a simulation. Musk, in particular, has stated that unless humanity is living in base reality, there is a high probability that we are in a simulation created by a more advanced civilization. Such statements have fueled popular interest in the idea, sometimes blurring the distinction between philosophical speculation and scientific evidence. But the central concern remains grounded in logical reasoning. The more realistic simulations become, the more difficult it becomes to deny the possibility that reality as we experience it could itself be simulated. Bostrom also acknowledges the ethical dimensions of his argument. If simulated beings are conscious, if they suffer, hope, learn, and love, then their creators bear significant moral responsibility. This brings the simulation hypothesis into dialogue with questions about artificial intelligence, digital sentience, and the rights of non-biological minds. If we someday build simulations as rich and detailed as our own world, will we be creating conscious beings? And if so, what obligations do we have toward them? Furthermore, the simulation argument forces us to consider our own future. If we believe we are unlikely to create ancestor simulations, does that mean we expect civilization to collapse before reaching that stage? If we reject that grim outcome, and also reject the idea that future civilizations will universally avoid simulations, then we are left to confront the statistical weight of the third possibility, that we are living in one. Interestingly, Bostrom himself does not claim to know which of the three possibilities is true. He maintains a position of epistemic humility, urging caution in drawing conclusions while emphasizing the philosophical value of the argument. In a sense, his goal is not to convince the world that we are in a simulation, but to reframe how we think about technological progress, existential risk, and the nature of consciousness. What makes the simulation argument so powerful is not that it proves anything definitively, but that it illuminates the logical structure of a possibility we can no longer ignore. It reveals how advancements in computing, artificial intelligence, and neuroscience are changing not only our capabilities, but our very understanding of reality. As we consider these implications, one question naturally arises: what might a quantum simulation look like? If classical simulations are already powerful, could a universe be rendered even more realistically using quantum information? Might quantum uncertainty, entanglement, and superposition be features of a simulation, not bugs in the system? If our universe behaves like a vast computation, as digital physics suggests, then a natural next question arises: what kind of computation could support such a universe? Is it classical, like the digital computers we use today, or could it be quantum in nature? In recent years, researchers have begun exploring this very idea, not only in theoretical physics, but also through real working systems designed to simulate quantum behavior using quantum devices. This is where the concept of quantum simulation enters the picture. It refers to the use of one quantum system to mimic the behavior of another, more complex quantum system. The goal is not necessarily to reproduce an entire universe in miniature, but to understand how quantum interactions unfold when direct analytical solutions are impossible. Yet, the implications reach far beyond the lab. If the universe itself exhibits quantum behaviors, uncertainty, entanglement, decoherence, then perhaps these are not merely natural features, but consequences of an underlying quantum computational substrate. To appreciate the significance of quantum simulation, we must first understand why classical computers struggle with quantum systems. The problem lies in scaling. A classical computer handles data using bits, binary units that can be in one of two states, 0 or 1. But quantum systems use qubits, which can exist in superpositions of 0 and 1 at the same time. Moreover, when multiple qubits are entangled, the total number of possible states grows exponentially. For instance, a system with 2 qubits can be in 4 possible superposed states. 3 qubits yield 8. 10 qubits give over 1,000, and the number doubles with each added qubit. Simulating such systems using classical resources quickly becomes intractable. By the time you reach 50 or 60 qubits, the amount of memory and processing power required exceeds the capabilities of even the largest supercomputers. This is not a theoretical limit, it is a practical one. Simulating quantum phenomena with classical computers becomes an exercise in approximation, estimation, and mathematical compression. But what if you could build a quantum simulator, a physical device that behaves according to the same quantum principles you wish to study? This idea dates back to physicist Richard Feynman, who in the early 1980s proposed that quantum systems should be simulated by quantum devices. His insight was elegant and profound. Instead of translating quantum behavior into classical terms, why not let nature do the work for you? If a device obeys the same physical laws as the system being studied, then it becomes a direct analog, a mirror in which to observe quantum phenomena with perfect fidelity. This idea has now become reality. Over the past 2 decades, researchers have built various forms of quantum simulators using trapped ions, superconducting circuits, ultra-cold atoms in optical lattices, and photonic systems. Each approach has its strengths, and each can be tailored to emulate specific quantum systems, such as spin chains, lattice gauge theories, or high-temperature superconductors. For example, in laboratories at institutions like MIT, Caltech, and the University of Innsbruck, physicists have arranged chains of trapped ions, charged atoms held in place by electromagnetic fields, to model the behavior of quantum magnetism. By carefully tuning the interactions between the ions, researchers can study how spins align or disorder themselves in various regimes. These experiments are not simulations in the Hollywood sense of virtual landscapes. They are physical processes governed by quantum laws, purpose-built to reflect the behavior of more complex or inaccessible systems. Similarly, in experiments involving ultra-cold atoms, scientists cool clouds of atoms to temperatures just above absolute zero and trap them in grids of laser light known as optical lattices. The atoms can then hop between sites, interact with neighbors, and form phases of matter that mimic the behavior of electrons in solids. These quantum emulators have been used to investigate phenomena such as the Mott insulator transition, Bose-Einstein condensation, and quantum phase transitions. Superconducting qubits, the same kind used in prototype quantum computers developed by companies like Google, IBM, and Rigetti, have also been adapted for simulation tasks. In 2019, researchers at Google claimed to achieve quantum supremacy, a milestone indicating that a quantum processor completed a task beyond the practical reach of classical machines. Though the task was abstract and not particularly useful on its own, it demonstrated the raw computational power of quantum hardware and laid the groundwork for more meaningful simulations. These advances in quantum simulation are not merely academic. They hint at a new way of understanding physical law, one that treats the universe not as a static set of equations, but as an evolving informational process governed by quantum rules. And this brings us closer to the idea that our universe itself might be a quantum simulation. Unlike classical simulations, which use binary digits and deterministic logic, a quantum simulation would operate using qubits, superpositions, and entangled states. This would explain why quantum phenomena appear so strange to us, because we are interpreting a quantum computational process through classical intuition. It would also offer a compelling rationale for the probabilistic nature of measurement, the emergence of decoherence, and the persistence of non-local correlations. Some researchers have speculated that quantum uncertainty could be a reflection of computational constraints, not noise or randomness, but the result of limited processing capacity at the foundational level. In such a model, only the parts of the universe that are observed need to be fully resolved, while unobserved regions remain in computational superposition. This is somewhat analogous to how a computer game renders only the portions of the environment that are currently visible to the player, conserving resources. Others have noted that certain features of quantum field theory and general relativity might emerge from a deeper quantum information architecture. For instance, in quantum error correction, redundancy is built into information encoding to protect against decoherence and noise. Surprisingly, some researchers have discovered that the mathematics of error-correcting codes appears in models of holographic space-time, suggesting that space itself might be a kind of quantum memory, safeguarded against loss. Physicists Seth Lloyd, Zohar Ringel, and Dmitry Kovrozhin have all explored models in which the universe operates as a quantum computer, running algorithms that evolve quantum states over time. Lloyd has gone so far as to estimate the total number of operations that the universe could have performed since the Big Bang, treating the cosmos as a finite computational device. These ideas remain speculative, but they rest on a solid foundation. Quantum information theory is not a fringe idea. It is an increasingly central framework in modern physics. The realization that entropy, entanglement, and observables are all informational quantities has transformed how we understand thermodynamics, gravity, and even cosmology. So, what would it mean if the universe were a quantum simulation? First, it would suggest that our reality is not continuous but discrete, with a finite amount of information contained in any region of space. This aligns with ideas from quantum gravity and loop quantum cosmology, which propose that space and time come in indivisible units. Second, it would imply that measurement, the act of extracting information, is fundamental to reality. Observers in this view are not external to the system, but embedded within it, helping to define its structure through interaction. Third, it would mean that probability is not just a reflection of ignorance, but a consequence of how the system resolves its own computational states. What we call randomness would be the frontier of computation, the cutting edge where potential becomes actuality. Fourth, it would frame the laws of physics not as immutable truths handed down from above, but as emergent properties of deeper algorithmic rules. These rules could, in principle, be modified, evolved, or reinterpreted in other simulations. This interpretation does not necessarily reduce reality to an illusion. On the contrary, it emphasizes the informational richness of existence. A quantum simulation is not less real than the base system it models. It is simply structured differently. If the physics we observe behaves as it does because it is running on a quantum substrate, then our task as scientists is to discover the rules of that substrate, not to deny the validity of our experiences within it. In the coming years, as quantum technologies continue to mature, we may be able to simulate larger and more complex quantum systems. These simulations could become laboratories for understanding not just exotic particles or rare phases of matter, but the nature of reality itself. And if we reach the point where we can simulate observers inside these systems, entities that process information, react, and perhaps even reflect, then we will be faced with a profound ethical and philosophical challenge. Are we simulating minds? And if so, how do we distinguish our own experience from theirs? If we truly are living in a simulation, whether classical or quantum, the next natural question is, can we detect it? Could there be telltale signs embedded in the fabric of our universe that betray its artificial origins? Is it possible to find empirical evidence, a measurable anomaly, or a built-in limitation that distinguishes a simulated reality from a base or non-simulated one? This question, once relegated to science fiction, is now being asked by serious physicists, cosmologists, and computer scientists. While no definitive test has yet confirmed or disproven the simulation hypothesis, a number of theoretical proposals and experimental ideas have emerged. These approaches attempt to identify physical phenomena that might point toward an underlying digital or algorithmic structure, what some researchers call simulation signatures. One of the earliest and most discussed proposals comes from physicist Silas Bean and his colleagues, who in the early 21st century suggested that a sufficiently detailed simulation of the universe might require spatial discretization. In other words, space would not be continuous, but divided into a lattice, a grid-like structure composed of tiny units. This is not unlike how digital images are composed of pixels, or how video games render environments using discrete points. Bean and his team reasoned that if the universe were simulated on a lattice with a finite resolution, then there would be observable consequences. Specifically, they proposed that high-energy particles, such as cosmic rays, might display directional dependence, a form of anisotropy, if they interacted with the underlying grid. In a universe without a preferred direction, cosmic ray particles should arrive uniformly from all directions. But in a lattice-based simulation, there could be slight differences depending on the orientation of the lattice with respect to the particle's motion. This idea led to the suggestion that we might look for energy cutoffs or directional anomalies in the behavior of ultra-high-energy cosmic rays. If such cutoffs exist and align with a regular pattern, they could serve as indirect evidence that space is discretized, and possibly that we are in a simulation. While intriguing, this hypothesis faces major challenges. The energies required to detect such anomalies are extreme, and data from cosmic ray observatories like the Pierre Auger Observatory in Argentina and the Telescope Array project in Utah have not yet revealed the predicted signatures. Still, the idea sparked further interest in the possibility of simulational constraints, physical limits that arise not from natural law, but from the boundaries of the computational substrate. Other researchers have considered whether the quantum indeterminacy observed in nature could reflect a form of resource management within a simulation. In this view, the probabilistic nature of quantum measurement is not fundamental randomness, but rather a way to conserve computational effort. Much like a video game engine renders only the parts of the scene visible to the player, a simulation might resolve only those aspects of the universe that are being observed or measured. This concept echoes the lazy evaluation techniques used in modern software development, where calculations are delayed until absolutely necessary. In the context of quantum mechanics, this could explain why particles appear to choose a definite state only when measured. The simulation does not compute the outcome until an observer queries it. If this were true, then certain types of delayed choice experiments, where measurement decisions are made after a particle has seemingly passed through a system, might reveal inconsistencies in how outcomes are rendered. So far, however, quantum experiments have consistently validated the standard framework of quantum mechanics. The phenomenon of entanglement, for example, does not appear to introduce any observable delays or inconsistencies, even when measured over vast distances. This does not rule out the simulation hypothesis, but it suggests that if we are in a simulation, it is extraordinarily well optimized. Another proposed test involves computational limits. Just as a computer simulation might struggle to represent certain scales of complexity or detail, a simulated universe might exhibit resolutions or bandwidth caps. These could manifest as limits on measurable quantities such as energy, information density, or entanglement. One example is the Bekenstein bound, which places a theoretical upper limit on the amount of information that can be contained within a finite region of space. According to this principle, the maximum entropy, or information content, of a region is proportional to its surface area, not its volume. This idea originally emerged from studies of black holes and thermodynamics, but it also aligns strikingly with the holographic principle, which we explored earlier. If this bound is not merely a physical constraint, but also a simulational one, then it could represent a kind of memory limit imposed by the computational substrate. Testing the Bekenstein bound directly is difficult, but researchers continue to explore its implications in quantum gravity, black hole thermodynamics, and information theory. Others have looked for evidence in the cosmic microwave background radiation, the afterglow of the Big Bang. If the universe was simulated, some argue, we might expect to find subtle irregularities or patterns in this ancient light, akin to compression artifacts in a digital image. While studies of the cosmic background have revealed some anomalies, such as the so-called cold spot, none have provided clear evidence of simulation artifacts. The observed features are still well explained by standard cosmological models involving inflation and dark matter. One more speculative avenue involves exploring irreducible complexity in the laws of physics themselves. If a simulation is the product of intelligent design, then its rules might be optimized for efficiency or symmetry. Redundancies, inconsistencies, or quirky constants might suggest that the rules evolved or were adjusted over time, perhaps through trial and error. On the other hand, a universe with perfectly elegant equations might suggest deliberate construction. Yet both natural evolution and intelligent design can produce elegant structures, so this line of reasoning remains largely philosophical. In addition to physical tests, some have proposed philosophical strategies for detecting simulation. For instance, some thinkers argue that if we can simulate conscious beings within our own technology, and if those beings show signs of awareness, creativity, or suffering, then we must take seriously the possibility that we ourselves are such simulations. This kind of reflexive reasoning, inferring from our own capabilities to our own origins, echoes the logic of the anthropic principle, which states that the universe must have properties compatible with the existence of observers. If simulation is possible and achievable, and if simulated minds are indistinguishable from non-simulated ones in their subjective experience, then we must consider that we are not uniquely biological or physical. However, this reasoning is not easily testable. It points to epistemological limits, boundaries on what we can know about the structure of our own existence. If a simulation is constructed to be indistinguishable from base reality, then detecting it may be fundamentally impossible from within. Some philosophers argue that the most likely way to discover we are in a simulation would be through communication, that is, contact or interference from the simulator. In this scenario, a simulated world might contain deliberate messages, anomalies, or encoded signals placed by its creators. These could be aesthetic, mathematical, or symbolic, messages in P, anomalies in prime number distributions, or self-referential signs embedded in physical constants. Yet no such messages have been identified with any certainty, and even if they were, distinguishing between natural coincidence and intentional design would be difficult. The line between discovery and projection is thin, and human pattern seeking is powerful. Despite these challenges, the search continues. Whether through experiments probing the limits of quantum theory, observations of cosmic phenomena, or philosophical inquiry, the question of simulation has become a legitimate area of exploration. It may not be answered by a single test or anomaly, but by a convergence of evidence, inference, and theory. More importantly, these inquiries encourage deeper reflection on what it means for something to be real. If the physical world behaves in exactly the same way whether it is simulated or not, then the distinction may be less meaningful than it appears. Simulation, in this context, is not about falseness or deception, but about structure and origin, about the processes and principles from which reality emerges. If the universe is indeed a simulation, classical or quantum, digital or analog, then a question looms above all others. What does this mean for consciousness? Are minds like ours simply computational artifacts, the byproducts of code and logic? Or is consciousness something more, something that resists simulation, transcending physical description altogether? The question of consciousness is ancient, yet it remains one of the most perplexing and unresolved in both science and philosophy. In recent decades, neuroscience and cognitive science have made tremendous progress in mapping brain structures, modeling neural circuits, and correlating mental states with physical activity. But despite these advances, the so-called hard problem of consciousness, as philosopher David Chalmers famously called it, remains stubbornly unresolved. The hard problem refers to the subjective nature of experience, the inequality of being, of seeing the color red, feeling pain, or contemplating one's own existence. While we can describe the neural mechanisms associated with these experiences, we cannot fully explain why they give rise to conscious awareness. What makes a system not just process information, but experience it? If we are to seriously consider the simulation hypothesis, we must confront this issue. Because a simulation is, by definition, a system that processes information according to predefined rules, it is natural to ask whether such a system can generate conscious experience. If the answer is yes, then the simulated mind is not merely an imitation, it is a thinking, feeling entity in its own right. If the answer is no, then simulated beings are philosophical zombies, machines that behave like conscious agents but lack inner experience. Some philosophers, including Chalmers himself, have suggested that consciousness could be substrate independent. In this view, what matters is not the physical makeup of the system, whether it is made of neurons or transistors, but the functional organization. If a system implements the right kinds of information processing structures, then it should give rise to consciousness, regardless of whether it exists in a biological brain or a simulated environment. This idea aligns with a computational theory of mind, which treats mental states as information states. The human brain, according to this view, is not fundamentally different from a computer. It is simply more complex and highly adapted for processing certain types of inputs and outputs. From this perspective, a sufficiently advanced simulation, one that models not only behavior but cognition and awareness, could generate real conscious minds. This view also fits naturally with the broader simulation hypothesis. If we can, in principle, simulate entire universes with rich physical laws, evolving environments, and intelligent life, then those simulated beings would be conscious if consciousness arises from computation. In this case, we, if we are indeed inside a simulation, are not fakes or illusions. We are real, sentient beings within an artificial cosmos. But not everyone agrees. Some argue that consciousness may require specific biological processes, for example, the complex interplay of biochemistry and electrical signals within neurons. Others suggest that quantum phenomena, such as entanglement and superposition within brain microstructures, may be essential. The most well-known theory along these lines is the orchestrated objective reduction (OR) model proposed by theoretical physicist Roger Penrose and anesthesiologist Stuart Hameroff. According to OR, consciousness arises from quantum computations within microtubules, tiny structural components found in neurons. These computations, the theory claims, are non-computable in the Turing sense and are sensitive to the fundamental structure of space-time. If true, this would imply that consciousness cannot be simulated using classical or even quantum computers because it involves a direct connection to the underlying fabric of the universe. While OR remains controversial and unproven, it serves as a useful counterpoint to the more widely accepted functionalist view. If consciousness cannot be reduced to computation, then no matter how realistic a simulation appears, it would lack true awareness. The simulated beings would be empty shells, like characters in a video game who follow scripts but have no inner life. This raises profound ethical and philosophical questions. If simulations can contain conscious minds, then running a simulation involves creating beings capable of joy, suffering, hope, and despair. The creators of such simulations bear moral responsibility, just as parents bear responsibility for their children or society for its members. But if simulations cannot produce consciousness, then simulated suffering is not real, and moral concerns vanish, along with any genuine meaning for the simulated beings. The stakes are high, because if we are in a simulation, then someone or something is responsible for the conditions of our world. And whether or not we are conscious determines whether our experiences matter. But there is another layer to consider: self-awareness. Consciousness is not just the passive experience of sights and sounds. it is also the awareness of awareness. We reflect, we question, we recognize ourselves in mirrors, recall past events, and imagine futures that have not yet occurred. This metacognitive ability is not easily reduced to algorithms. Even among artificial intelligence systems, which can now process language, images, and tasks with remarkable accuracy, genuine self-awareness remains elusive. Cognitive scientist Anil Seth and others have argued that consciousness is best understood as a form of controlled hallucination, a predictive model that the brain generates based on sensory input, memory, and internal expectations. This model constantly updates itself, balancing incoming data with prior beliefs. In this view, the brain does not passively receive the world, it actively constructs it. If consciousness is a simulation of the external world created by our brains, then the idea that we live in a larger external simulation becomes intriguingly recursive. The simulated brain simulates the perceived world, which may itself be a simulation created by something even more fundamental. Consciousness, in this sense, is not just a window onto reality, it is a model built within a model. This leads us to an important philosophical question. If consciousness is embedded in a simulation, can it ever know the truth? Can a mind that exists within a system discover the nature of the system itself? Or are there built-in epistemic limits, boundaries on what can be known from within? This dilemma is reflected in Gödel's incompleteness theorems, which show that any sufficiently powerful formal system contains statements that are true but unprovable within the system. By analogy, our conscious minds may be incapable of fully grasping the nature of the simulation they inhabit, just as a character in a novel cannot read the author's mind, or a computer program cannot modify the processor that runs it. Still, we try. Whether through science, philosophy, or introspection, humans have always sought to understand the framework in which they exist. And whether we are biological or simulated, conscious experience seems to be our most immediate and undeniable reality. We may question the world, the self, and the source of both, but we cannot deny that something is happening. This, perhaps, is the greatest mystery of all. That regardless of whether we are carbon-based life forms or patterns of data in a quantum grid, we feel, we think, we ask questions that our origins may never have prepared us to answer. As humanity steps deeper into the 21st century, we find ourselves on the threshold of a technological revolution unlike any that came before. This revolution is not powered by steam or electricity, nor by silicon chips in their classical form. It is driven instead by the principles of quantum mechanics, the same principles that once baffled Einstein, Bohr, and Schrodinger. At the center of this transformation is quantum computing, a field that not only promises to reshape industries and solve previously intractable problems, but also offers a lens through which we might explore the very architecture of reality. Quantum computing is not simply a faster or smaller version of classical computing. It is a fundamentally different model of information processing, one that uses the rules of quantum mechanics rather than the deterministic logic of binary code. And if our universe itself is structured like a quantum simulation, as we have explored in earlier sections, then building quantum computers may be our closest approach to mirroring the logic of the cosmos from within. To understand why quantum computers are so different, we must begin with their basic unit of information, the quantum bit, or qubit. Unlike a classical bit, which can be either 0 or 1, a qubit can exist in a superposition of both states simultaneously. This means that a single qubit encodes not just one value, but a combination of values, weighted by quantum amplitudes. The true power of quantum computing emerges when multiple qubits are combined into a system. Due to entanglement, qubits can become deeply interconnected, such that the state of one instantly influences the state of another, regardless of the physical distance between them. This entanglement enables quantum computers to perform certain calculations in parallel, exploring many possible solutions at once. But it is not just parallelism that makes quantum computing powerful. Quantum algorithms, like Shor's algorithm for factoring large numbers or Grover's algorithm for database searching, exploit interference patterns in quantum amplitudes to amplify correct answers while cancelling out incorrect ones. In essence, quantum computation does not merely try all paths, it guides probability toward the solution. This computational paradigm is not just a theoretical curiosity. Major technology companies, including Google, IBM, and Microsoft, along with academic institutions and startups, have built working quantum processors, though still in the early stages, often limited by noise, coherence time, and error rates. These machines have already begun to demonstrate what is known as quantum advantage, the ability to solve specific problems that classical computers cannot solve efficiently. In the context of the simulation hypothesis, quantum computing takes on a new layer of significance. If the universe is governed by quantum rules, then it makes sense that our most powerful computational tools would also follow those rules. Just as a musical instrument resonates most naturally with its own harmonic frequencies, a quantum computer resonates with the underlying logic of a quantum universe. This leads to a provocative idea. Quantum computers may not just simulate reality, they may operate within the same logical framework as reality itself. Unlike classical simulations, which approximate quantum behavior using enormous amounts of data and time, quantum computers are natively quantum. They do not imitate interference and entanglement, they use them. Physicist David Deutsch, one of the pioneers of quantum computing theory, has long argued that quantum computers reveal a deep truth about the nature of the multiverse. According to his interpretation, when a quantum algorithm runs, it does not merely compute faster, it taps into parallel universes where all possible paths of computation unfold. From this perspective, a quantum computer is not just a machine, it is a window into the structure of a multiverse. Whether one accepts this interpretation or not, the implications are vast. If quantum computation is indeed a reflection of the universe's own architecture, then building and studying quantum computers may teach us more than just how to break encryption or simulate molecules. It may reveal how and why the universe behaves as it does. Already, researchers are using quantum computers to simulate quantum field theories, topological phases of matter, and quantum gravity models. These are not easy problems. Many involve enormous state spaces and intricate interactions that defy classical computation. But quantum simulators, devices that do not necessarily perform general-purpose computations, but are finely tuned to model specific systems, are beginning to provide insights into problems once considered out of reach. For instance, scientists are now exploring how to simulate black hole evaporation, entanglement entropy, and ADS-CFT dualities using quantum circuits. These simulations could one day help resolve paradoxes in theoretical physics, such as the black hole information problem, or illuminate how space-time geometry emerges from quantum entanglement, ideas that connect directly to the holographic principle and digital physics. Even more speculative are proposals to use quantum computers to test the foundations of quantum mechanics itself. Certain interpretations of quantum theory predict subtle differences in how quantum information should behave, differences that might be detectable only at the scale and precision afforded by quantum computation. If we can program quantum systems to behave in ways not currently predicted by our models, we might uncover signs of new physics, or even of an underlying simulational framework. Imagine, for example, a quantum computer so powerful and precise that it begins to encounter systematic deviations from expected behavior. Perhaps these deviations reflect hidden constraints, limits in the fidelity of the underlying simulation. Perhaps there are thresholds of entanglement or complexity beyond which the simulation cannot sustain coherence, revealing artifacts of the computational substrate. While purely speculative, these ideas are now being seriously entertained by some physicists as part of the broader effort to probe the foundations of reality. Another intriguing possibility is that quantum computers could create new simulated worlds, virtual environments governed not by classical rules, but by quantum ones. In such environments, artificial agents could interact, evolve, and even perhaps attain forms of proto-consciousness. These worlds would not be simulations of our universe, but simulations like our universe, sharing its probabilistic and entangled structure. If such worlds are possible, then our own universe may be just one instance in a vast landscape of quantum simulations. Each simulation may contain its own laws, particles, and observers. Each may evolve in parallel according to the same quantum logic. And some of them, perhaps ours, may attain sufficient complexity to question their own nature, just as we are doing now. This recursive possibility that a quantum simulation can contain beings who themselves build quantum simulators is a profound one. It suggests that the search for truth may be an infinite regress, a hall of mirrors where each layer of reality reflects and contains another. It also forces us to reconsider what it means to be real. If we build a quantum world rich enough to support awareness, how would its inhabitants view us? As gods, as developers, or as unknowable forces beyond comprehension? At the same time, the practical development of quantum computing demands caution and humility. These machines are still fragile, error-prone, and highly specialized. Building a large-scale, fault-tolerant quantum computer remains one of the greatest engineering challenges of our time, but the progress is undeniable. Year by year, coherence times are improving, error correction schemes are evolving, and qubit counts are increasing. Some researchers believe that within a few decades, we will reach the threshold where quantum computers surpass all classical systems in solving a broad range of scientific problems. Others warn that practical quantum computing may remain limited to niche applications, but even limited success could yield profound scientific and philosophical dividends. Ultimately, the significance of quantum computing goes beyond computation. It represents a new way of thinking, a shift from deterministic cause and effect to probabilistic inference, from isolated systems to entangled networks, from static reality to evolving information. In this new paradigm, simulation and reality are not opposites but partners, two aspects of a deeper, more dynamic universe. Among the greatest unanswered questions in science is the question of life itself. How did it begin? How did a universe governed by simple laws and impersonal forces give rise to organisms that move, sense, grow, reproduce, and eventually wonder? The origin of life is a topic that spans biology, chemistry, physics, and philosophy. But within the context of a simulated universe, particularly one rooted in quantum information, this question takes on new and provocative dimensions. Could life, as we know it, be the result of programmed parameters within a computational framework? Or is it an emergent feature of any sufficiently complex system, whether real or simulated? The traditional scientific approach to the origin of life focuses on abiogenesis, the idea that life arose naturally from non-living matter under the right conditions. This process is thought to have occurred on early Earth, where the right mix of water, heat, energy sources, and organic molecules may have given rise to self-replicating chemical systems. Over time, these primitive systems evolved into the first simple cells, which in turn gave rise to the astonishing diversity of life we observe today. Numerous theories have been proposed to explain the mechanism of this transition. The RNA world hypothesis suggests that ribonucleic acid, capable of both storing information and catalyzing chemical reactions, may have been the first building block of life. Others point to hydrothermal vents on the ocean floor, where mineral-rich fluids and thermal gradients could have created the right conditions for molecular complexity. Still others propose metabolism-first models in which networks of chemical reactions became self-sustaining before genetic materials emerged. All of these theories share a core assumption that the universe is governed by consistent physical laws and that life emerged as a consequence of those laws playing out in a chemical context. But if the universe is a simulation, particularly one that encodes and evolves according to rules of quantum information, then new possibilities emerge. Life might not be a random outcome of chemistry. It might be an expected or even intended feature of the system's design. Let us consider this possibility carefully. In computational simulations, especially those involving artificial life, simple rule sets can lead to the spontaneous emergence of lifelike behavior. Cellular automata, agent-based models, and evolutionary algorithms have all demonstrated that under the right conditions, simulated systems can develop structures that move, replicate, adapt, and compete. These behaviors are not programmed explicitly. They arise emergently from the rules and initial conditions. In this context, life is not something added to a system. It is something that emerges when complexity crosses a certain threshold. If our universe is itself a simulation, then life might be no more surprising than the appearance of gliders in Conway's Game of Life, or the evolution of creatures in digital ecosystems like Tierra or Avida, simulations in which digital organisms mutate, compete, and evolve. But there is a deeper layer to consider. In digital systems, Evolution depends not just on initial complexity, but also on information flow, feedback mechanisms, and selection pressures. The environment must store and transmit information. Changes must be preserved, evaluated, and amplified. These are not mere accidents. They are consequences of the system's capacity to support dynamic, self-modifying processes. In a universe governed by quantum information, similar principles may apply. Quantum entanglement, superposition, and decoherence offer mechanisms by which information can be stored, transferred, and transformed. Some researchers have even proposed that quantum effects may have played a role in the origin of life, offering computational shortcuts or enabling non-local correlations that boosted the efficiency of early biochemical reactions. For example, certain proteins appear to exploit quantum tunneling to move particles across energy barriers. Photosynthesis in plants and bacteria involves quantum coherence, allowing excitons, energy packets, to explore multiple paths and choose the most efficient route. Even in the human brain, some theorists have speculated that quantum processes may contribute to the binding of information across neurons, though these claims remain contentious. Still, the mere fact that biological systems can sustain quantum effects in warm, wet environments suggests that life and quantum information are not incompatible. On the contrary, they may be deeply entwined. If the substrate of the universe is quantum computational, then life may be the self-organizing manifestation of quantum information seeking stable, self-replicating configurations. From this vantage point, the emergence of life is not miraculous, it is natural. The simulation, if such it is, does not need to be programmed with every species or behavior. It only needs to include rules that favor complexity, adaptability, and feedback. Once those conditions exist, life becomes not just possible but probable. Yet this line of thinking opens the door to another possibility, that life, or the conditions for life, were deliberately encoded into the simulation. Just as programmers design artificial life simulations with goals or constraints, the architects of a universal simulation, if they exist, may have seeded it with parameters that encourage biological emergence. This does not require supernatural intent. It may be as simple as a research objective to observe how life evolves in various computational environments. This idea bears resemblance to the concept of directed panspermia, proposed by Francis Crick, co-discoverer of the structure of DNA. In that hypothesis, life on Earth was seeded intentionally by an advanced civilization. The simulation hypothesis, extended in this direction, suggests that not only was life seeded, it was simulated into being, along with the environment it inhabits. Of course, such claims are speculative, but they are not wholly outside the bounds of scientific reasoning. If we accept that advanced civilizations might develop the capacity to simulate entire worlds, then creating ecosystems, or even entire biospheres, becomes feasible. In this light, life is both a product of rules and a potential feature of design. This also raises important ethical and existential questions. If we are simulated beings, is our consciousness real? As we explored in the previous section, if functionalism holds true, then consciousness depends on organization, not substrate. And if that is the case, then our experiences, emotions, and relationships are just as meaningful as those of any being in any reality. But what about the meaning of life itself? Does living in a simulation render life less valuable or more? In some ways, the simulation hypothesis challenges the traditional notion of purpose. If we are part of a simulation, then we may be part of an experiment, a game, or a study. But this does not necessarily diminish our agency. On the contrary, meaning is something we create, not something imposed from outside. Whether the universe is natural or simulated, we still face the same questions. How should we live? What do we value? How do we treat one another? Moreover, recognizing the informational basis of life may deepen our appreciation for its complexity. DNA is not just a molecule, it is a code, a language written in 4 bases, capable of storing enormous quantities of information. Proteins are not just structures, they are machines, assembled with precision and adapted through millions of years of evolutionary feedback. The brain is not merely an organ, it is a network, processing patterns, creating models, generating narratives. If this is all part of a simulation, then it is a remarkably elegant one. It has rules that produce stars and galaxies, but also butterflies and music. It sustains life long enough for that life to wonder, question, and dream. Whether that speaks to a higher purpose or simply to the power of emergent complexity is a matter of interpretation. In our own time, researchers in synthetic biology are beginning to reverse engineer the origin of life. By assembling genetic circuits, designing artificial cells, and programming biochemical behavior, they are inching closer to creating new forms of life, forms that may someday transcend biology altogether. This is not just science fiction, it is an unfolding reality. And as we simulate life, we begin to ask, are we following a path or retracing one? Are we inventing life anew or reenacting a process that once created us? The simulation hypothesis, at its most provocative, suggests that we are creators within creation, writing simulations inside a simulation, building life from the building blocks of life itself. After traveling through quantum uncertainty, computational theory, philosophical logic, and the origins of life, we now arrive at a moment of reflection. The idea that we might be living in a simulation, once relegated to science fiction, has evolved into a legitimate question at the frontier of science and philosophy. It challenges our assumptions about reality, identity, and truth. But now we must ask, what are we to make of it all? Is the simulation hypothesis a plausible scientific theory, a compelling philosophical argument, or an elaborate metaphor for human curiosity? Let us begin by reviewing the terrain we have crossed. The earliest questions about reality came from thinkers like Plato and Descartes, who asked whether the world we perceive could be an illusion. With the rise of quantum mechanics, those questions took on a new dimension. Experiments like the double slit and principles such as superposition, entanglement, and decoherence revealed that reality at its deepest level is far less concrete than it appears. The emergence of digital physics further expanded this view, proposing that the universe itself might be computable, governed by algorithms, evolving through discrete steps. From simple rules in cellular automata, we saw how complex and lifelike behavior can arise, suggesting that consciousness and biological evolution could be emergent phenomena in an informational substrate. Simulation became not just a philosophical speculation, but a framework grounded in mathematical logic, information theory, and computational modeling. Nick Bostrom's simulation argument then provided a sharp, probabilistic formulation. If it is possible to simulate conscious beings, and if advanced civilizations have the will and capacity to do so, then the number of simulated minds could vastly outnumber the biological ones. If this is the case, then it is statistically more likely that we are among the simulated minds than among the original creators. Quantum simulation, quantum computing, and quantum information theory have only deepened this narrative. They suggest that not only is the universe governed by quantum logic, but that it may be constructible using quantum devices, possibly even mirrorable using machines that process information the same way the universe does. And as we simulate quantum systems, life processes, and even neural networks, the line between physical and virtual, between matter and information, begins to dissolve. But where does this leave us? The first and most important point is that we do not know whether we are in a simulation. There is no conclusive experiment, no logical proof, no observed glitch that demands we accept this idea as fact. The simulation hypothesis remains a hypothesis, a speculative but carefully constructed possibility. However, the simulation hypothesis is not meaningless. On the contrary, it serves as a powerful intellectual tool, a framework that forces us to re-express old questions in new terms. It prompts us to ask what counts as evidence, what qualifies as consciousness, and what defines reality. It compels us to think about the limits of knowledge, not just in terms of what we can see or measure, but in terms of what we can ever access from within a system. In this way, the simulation hypothesis echoes the Copernican principle, which states that we should not assume a privileged position in the cosmos. Just as Earth was once thought to be the center of the universe, we may be tempted to believe that base reality is something we occupy. The simulation argument reminds us that this assumption may be unjustified. At the same time, it is crucial to distinguish between scientific speculation and philosophical overreach. The tools of science rely on testability, predictive power, and falsifiability. As of now, there is no clear path to experimentally confirm or disprove the simulation hypothesis. Any evidence we might find, such as quantized spacetime or anomalous cosmic data, could be explained by natural models that do not require simulation. This leads some physicists and philosophers to conclude that the simulation hypothesis, while interesting, is not currently a scientific theory. It may belong to the realm of metaphysics, a speculative overlay to the physical models we build. Others argue that even untestable ideas can be fruitful if they generate new ways of thinking, inspire novel hypotheses, or expose hidden assumptions in our worldview. There is also the risk of psychological distortion. The simulation hypothesis, when taken too literally, can lead to solipsism, the belief that only one's own mind is sure to exist, or nihilism, the belief that life lacks meaning. If everything is a simulation, one might ask, then what is the point? But such conclusions are not only unwarranted, they are based on a misunderstanding of what simulation implies. Whether or not the universe is simulated, our experiences are real. Pain, love, learning, beauty, and curiosity are not illusions. If consciousness arises from structure rather than substance, then our inner lives are no less valid than those of any biological being. Meaning is not dictated by whether the cosmos runs on silicon or carbon, but by how we choose to engage with it. Indeed, if we are simulated, then everything we do matters more, not less. Every act of kindness, every scientific discovery, every artistic expression becomes part of a broader tapestry, possibly being observed, recorded, or even learned from by entities beyond our comprehension. In this way, the simulation hypothesis paradoxically affirms the significance of human action. It also reframes the future. As we develop our own simulations, using artificial intelligence, virtual reality, and quantum computing, we take on the role of creators within creation. We are not just exploring the nature of simulated worlds, we are building them, and with that comes a profound ethical responsibility. If consciousness can emerge in simulated systems, then we must consider the welfare of the beings we create, even if they begin as lines of code. This moment in history marks a convergence of fields that were once separate. Physics, information theory, computer science, neuroscience, and philosophy are now entangled in a shared inquiry. That convergence may be the most important sign that we are moving closer, not necessarily to knowing the ultimate truth, but to asking the right questions. Are we living in a quantum simulation? Perhaps. Or perhaps the very act of wondering about it is what matters most. It reveals that consciousness has reached a level of self-awareness capable of interrogating the conditions of its own existence. Whether we are flesh or code, light or logic, we are minds in motion, struggling to map the unknown, to understand what lies beyond the veil, to grasp the source of the laws that govern our universe. And so, in the spirit of curiosity, we end not with an answer but with an open door. For whether we live in a simulation or not, the cosmos invites us to explore, to imagine, and to seek. And that journey of discovery, doubt, and wonder is as real as anything we can ever know. As anything we can ever know.